Hello, Firoza. Good morning.
Yes, good morning, sir. Sir, I'm just sharing you the privilege to be the presenter.
Yeah, sure. And I will share my screen now.
Yes, sir, so did you share your screen?
No, no, not yet.
No, yeah, okay.
Is this okay?
Yes, sir. Yes, sir. Everything is fine, sir.
Sure.
Thank you, sir.
No, good.
Yeah, sir, should we start or should we wait for another 2 or 3 minutes? Like we have already notified all the participants.
Yep, we can wait for a couple of minutes,
Yeah. Okay.
or we can start in 5 minutes, 10:05.
Okay. Okay. Thanks. Thank you, sir. Yeah. Can we start, sir?
Sure.
Okay. Thank you, sir. So just one announcement I will just give to the participant. All the participants are requested to please note that today the validatory session is from 3 to 3:30 p.m. So please be connected with us. Thank you.
Good morning, everyone, and welcome to day 10 workshop for Embedded UVM. And so we are coming to a closure now. I hope it was a pretty productive workshop for all of you. So today we'll be discussing on Intel FPGAs for AI and data center. So I'll be talking about how Intel FPGAs are uh, are becoming part of our digital revolution and how we are helping our customer or our ecosystem to leverage the next generation of data center disruption or digital disruption coming forward. So we'll get started with that. And also today I'll be uh, explaining or I'll be showing you the dev kit farm or the dev cloud which we have which Larry introduced. So I'll be giving some demo on that with running some example designs. This is agenda for today's talk. We'll be providing introduction to Intel FPGAs and acceleration solutions. So we'll be more focusing on the FPGAs for the data center and AI applications. While for the embedded, we already covered in day 2. For then we'll then cover FPGA hardware accelerator for high performance computing workloads. Then Intel FPGA software development kit for OpenCL tools and its usage. Development flows for acceleration stack. So in next 2 hours, we'll be covering all these sections and it'll be interesting for you to know that how Intel as a company, along with the FPGA portfolio, we're trying to solve some complex problems. Let's move. Let's take a deep dive into the first section. That is the acceleration solutions and how Intel FPGAs fit into this the story of the acceleration or data center acceleration as such. So traditionally, we there are accelerators and there. So basically, when we talk about acceleration, so it's all about heterogeneous computing, and so we and when we talk about heterogeneous computing, so that consists of multiple uh, computing devices working seamlessly. So then it's all revolving around the host CPU, and we have dedicated accelerators like ASSPs or ASICs, which actually perform the fixed functional acceleration and which are actually for maximum compute efficiency, low power, or you can say with stable functionality. But the problem is with the ASIC or the ASSPs are once they are built, they cannot be modified when they're on field. So that means you need to have a hardware respin or you need to have a completely entire different hardware altogether. And in this evolving digital world, there are a lot of changes happening. I would say the transformation is taking to a rapid change. And as we speak, there are a lot of changes happening around the world. And to catch up this, ASIC sees some challenges to, like for example, time to market. Start building a chip today, and until the chip is released and in production, the specifications would have already changed. So that are some of the uh, limitations of dedicated accelerators. Then we have FPGA and GPU, where we call it as versatile accelerator because you can actually change the functionality on the field. That is, once it is deployed, you can actually go back and say, hey, this is the model, like for example, in AI, the model which I'm implementing, and I go back and say, I want to change something there. I want to have multiple layers, or I want to change the model altogether itself. So still, there's a room where you can actually have the accelerator built and a custom for a custom workload. So question is, what are FPGAs? Why do you like? What do you mean by FPGAs? So FPGAs are like, if I have to spell it, it's field programmable gate arrays, and we have been looking into this FPGAs since entire for this workshop, and we spoke about on day two we covered about uh, various FPGA studios from. We also deep dived into architecture of Cyclone architecture, that's FPGA plus SoC. So altogether, to summarize them, so FPGAs are uh, FPGA comes with millions of logic elements. Logic elements contain they are the heart of the computing resources, you would say. Plus, they are the computing fabric. Uh, typically today's FPGA come with a lot of embedded memory blocks and thousands of DSP blocks, where we also discussed in our previous sessions about how hard floating point DSPs enable you to implement multiple workloads like wireless, wireline applications. So DSPs are the main core features of FPGA, and they're a building block of today's next generation FPGAs. FPGA contains, or they consist of programmable routing elements, and this is why FPGA makes it as an programmable device. This is something like a core feature, because you can reroute and you can reprogram the routing of the FPGA resources, uh, that that provides you the flexibility to implement any algorithm into the FPGA, right? So, and we have high-speed transceivers, and they are very important in today's computing scenarios. Typically, in data center, you have multiple racks, and they're all they're all interconnected together to a backend fabric, and it's all possible. And if you want to have an FPGA into the data center, high-speed transceivers really enable us to have this connectivity part. Then we have hard IPs. Uh, Typically, hard IPs are, for example, PCI. Again, that is on top of the high-speed transceiver. So the 5 physical layer is implemented in transceiver, while the upper layers are also provided as a hardened IP. Now that really makes sense for someone who is going to use an protocol which is high speed and really doesn't want to invest time and invest the resources which are there in the FPGA to implement that protocol. So this hardened IP enables customers or anyone using FPGA to uh, leverage the FPGA capabilities along with fixed protocol implementation, which is already provided in the silicon. And altogether, if you see this, uh, you take logic elements, memory blocks, DSPs, programmable routings, transceivers, and hardened IPs like Ethernet, PCI, and so on and so forth. So you bundle it all together, take the FPGA, and you create your own custom hardware, and that is your accelerator of your choice, not the accelerator of your vendor actually. So you get more flexibility in implementing what you desire, and from the academic perspective, where we always have the research front forwarding the industry, we say. So this enables you lot to you to explore a lot of architectural features and implement next generation of computing technologies. So then we now understood what are FPGAs, but then why are FPGAs very critical? why they are good fit for an accelerator, because reprogrammable, as I just discussed, that the routing elements are programmable. That, that allows us to reprogram the FPGAs on field, gives you more flexibility. You design and deploy one implementation today and change it tomorrow. So then we have inherently parallel architecture. So we'll be discussing those, like why does how does this parallel architecture helps in subsequent slides. But yeah, to give overview here. So uh, interestingly, as a FPGA device, they're already parallel, because you get thousands of DSP blocks and millions of logic elements all together bundled in FPGA, and they're all open for you to program it. You can build multiple pipelines, and those pipelines are all running on parallel. They can run on different clocks. So that makes them already parallel, and they're a good fit for parallel computing. Next is high performance. Yeah, because since you implement your algorithms parallelly and you have multiple pipelines, you can actually have those high performance algorithm, or you can say FPGAs are high performance devices. And as we discussed now, FPGAs are flexible, and they're low latency, because you can build a pipe from, or you can build a pipeline from the data entering into FPGA and leaving out of the FPGA, which is programmable and which you can control over it. So you don't need, there's not a dependency on your clock cycle or your instruction cycle as such. You can have multiple of instruction cycles implemented parallelly, and that in turn provides you a low latency implementation. And of course, energy efficient. These devices are energy efficient in terms of performance per watt. So if you take any implementation of a high speed uh, algorithm, for example, FFT in case or DFT in case, so if you compare performance per watt, so that's really uh, competitive, or really, I would say, comparable to other architectures like GPU and CPU. Yeah. So next is we're going to talk about what are different application areas for acceleration from edge to cloud. This is a high level. We'll go to deep in a couple of slides next. So uh, yeah, for us now to understand is where this acceleration sits or is good fit for. And I would say the answer is it fits all the way from edge to cloud. Uh, like for example, you have a smart factory, and FPGAs are sitting on the factory floor. For example, for IO expansion, where you connect multiple protocols like SPI, I2C for controlling multiple sensors like temperature, pressure, and different actuators and motors. So FPGAs are there in on the field from decades and from a couple of decades long back, and that is where we call it as embedded. So because they're part of your embedded system, they're there on your machines there. So that's one of the applications of the FPGA. And there, and when you say that, why do you need an FPGA in embedded? Because you want to offload some of the tasks from a CPU or a microcontroller to FPGA. So that's the embedded part. And then the edge computing, in case of, say, you have multiple data coming into multiple machines, and you want to aggregate it, and before sending it to the cloud, you want to compute it in the factory itself, and which we call it as edge. So that becomes an edge computing application, and FPGAs are a good fit for it. There has been a wide adoption in network infrastructure, and not just today, not just for acceleration, but it has been there uh, from a quite a long time. For example, if you have to make a call around today, uh, there are chances, or I would say, the call goes through an FPGA device, right? So you would, but definitely as a user, you don't really need to know about it. But as an from a technical perspective, FPGAs are there in network domain, and they're already there in telecom domain. But then we'll also see next how it's enabling for 5G and the next generation technologies. Then for data center and cloud, a lot of examples will be seeing today. So I'll be not talking too much right now because subsequent slides are going to cover all about the data center applications. So what are the functionalities which someone can implement using an Intel FPGA and an FPGA programmable acceleration card? And this is like not limited to your imagination. So uh, this is only a few of them which are just displayed on the slide, but uh, there is a plethora of application areas where FPGAs are being deployed today. So one of them is data analytics. So uh, again, we'll have a look of how it's shaping our data center workloads in doing data analytics. But to give a rough or a high level overview, data analytics is where you have a huge data and you want to visualize it or realize that data into some sensible part. And now, while doing that, there is a lot of computation done there. Like, for example, you need to format that data. Like the data is split across the multiple formats. You want to massage that the data to a unified format where your algorithms can understand. So that's the first part of data analytics, and this where FPGAs are used today. A lot of FPGA implementation happening across that. May it be Apache Spark or Cassette, or I would say for database acceleration, it might be Cassandra acceleration, NoSQL, for example. So they're all part of the data analytics implementation, and where FPGAs are playing a major role there. So the edge processing, I just give an example about how a smart factory can be uh, can use FPGAs. And security, there are a lot of demand of having FPGAs into security applications because uh, today the network usage has gone multiple folds, and as we are today, like today we are doing a virtual workshop, so the demand for data has shoot up, and not only during this COVID, but still it's been there. We see the rise in data creation as well as data consumption. So both of them are happening, and it's going to continue. So the security of the data, how well someone can manage the data, not only their own but customers' data, someone else's data. So so that is important. How do you protect your data? So and there FPGAs are helping because you want to monitor the packets coming into your network, and you don't want to lose any packet because a lost packet can be a vulnerable or a threat packet itself. So FPGAs provide a very robust implementation of this security. Maybe it is a firewall or something like rule-based security features or algorithms. So they're all very much useful, or they're very much implemented in FPGAs in today's world. Next is scientific computation. And for today's scenario, when we have a global crisis in terms of healthcare or a pandemic, we call, so there. is a demand, and it's a responsibility, I would say. It's not someone is doing for profit, or we're not doing it for sake. We're all together fighting this against the pandemic. Everyone is concerned. So scientific computation is really important uh, for today's world, as well as in the future. We're just going to be even more focused on it. We don't want next pandemic to happen for definite. But so for that, FPGAs can help, and I'm sure about it. We have FPGA based acceleration for uh, genome acceleration, genomics. We have a partner. I have a slide on that. I'll be talking about it. So that's very interesting, and we've been doing it for a long time, and we'll be continuing it to enable multiple partners, research institutes, and anyone wants to research in or scientific computation is a noble area, and I think FPGAs are significantly computing today, or significantly uh, having a major role in this area. And I think I spoke about database access in the data analytics. I just give a brief overview of like how Cassandra and NoSQL is being accelerated. Then AI, we are doing it a lot on AI. Vikas will be talking today on that more about how FPGAs are being implemented for next generation AI deployments. Then video processing, it's been there from decades. We've been doing this for broadcasting, may even for uh, cameras and video rendering, multiple channel multiplexing, and all those processing, video processing as such, the traditional again best suited for FPG. NVF, uh, that's a network functional virtualization and infrastructure management. That's another interesting topic, which will be slightly covering in subsequent slides. But again, so the idea of this slide is like you have this multiple workloads, and just on the left hand side, you see it's just one FPGA. Just show the pointer here. Yeah. So we just have an FPGA card, which actually, by the way, can do all these different workloads. So just that is what I want to emphasize is the FPGAs are versatile in nature, right? So we'll be seeing that in the green color AFU, and how to build it yourself. Also, we'll be seeing that. Let's move further. Like we'll a little bit about now technicals. Okay, so now we saw application areas. We know we're all set. Okay, uh, what's the role of FPGAs and how it's enabling making our world safer and world more uh, compute or solving the compute challenges. We just saw it. Now let's move to like a little bit of how do you see as an accelerator as with FPGAs and why they're unique. So one of the questions, yes, we answered those questions in previous slide, but let me give an example. Like for example, in this case, uh, the first step is you see on the left hand side is the processor, and let's take an example. It's an Intel processor. Uh, for example, let's take it as a Xeon processor, and you want to do say, okay, in this COVID situation, and once, of course, we are all opening up, and we're going to uh, places like malls, and of course, you need to buy groceries, and also you need to go to a mart. So let's take an example in this case. Okay, so you want to build a social distancing application using a camera. So what you do is you start with a processor and you attach camera, maybe one camera or multiple cameras, and you implement an AI algorithm saying, okay, first is you detect a person. That's the first basic thing you do. Say, okay, so you detect a person. let's say, take an example, you use a YOLO software, which is an object detection algorithm. So you take that, implement it, and of course, and then you create a geometric boundaries and say 6 feet across person. You don't want to see another person coming in that geometric boundary, and you want to find it. And the next layer is your that implementing that geometric boundary and then doing that calculation of 6 feet. So you would write this code and deploy it in a typical processor, and which has a memory attached. And then what you see is, uh, okay, I would say one camera, couple of cameras are working good, but then I want to do it as a real time. I don't want to miss any person. I don't want to miss any frame in that. And because this is important to make sure that I even write alarm and protect people from not coming closer. So you have a good intent and you want to make sure that your implementation is a robust. So and then what you see is there you see, okay, you do something called profiling, and you found that there are some frame leaks happening, few frames are dropping away. So you want to you saw that it is because of one of the core taking some time to implement one of the, say, matrix multiplication in one of the layer, and you really found that there's something happening there, and there's some bottleneck happening between this memory where data is coming and going from the processor to the memory back and forth, and I see there's some bottleneck. Bandwidth is not really is getting constrained. So altogether, on a high level, you see there's frame drop. So what is the best option next to go is you attach a FPGA device. Now, uh, now you attach this FPGA device using a PCI. It can be a PCI, and what you do is you implement few of the layers which are getting bottleneck here into this, and you offload few of the matrix multiplication logic to be implemented in FPGA, and let the memory in the FPGA, which is attached to the FPGA, be used to compute those layers. And you don't want to use this, so that uh, this memory can be efficiently used for the next video pipeline. So, or to get the next frame. So that way, with this look aside acceleration, you got a good performance, or you boosted your performance, and then you were able to get, for example, more cameras into the same hardware, or without, or with the same number of cameras, the frames were not dropping. So this is a typical use case which I explained, and with that use case, I explained you how a look-aside acceleration works. So look-aside acceleration means there's a FPGA which is attached to the processor, and the processor is the main module which actually has the data, which pushes the data to the accelerator. Once the accelerator completes the function, it gets back the data, and then this processor completes its entire functionality. So the main compute unit is a processor in this case. So let's see what is inline processor. Now, in the earlier case, the camera was attached to a processor. Now, still, you say, okay, fine, for a decent amount of a grocery store or a supermarket, which is a mid-size, okay, my processor attached cameras. So because cameras may be connected to, say, USB hub, or they are connected to a DVR, and then you get the data back to the CPU. So that's the channel which we discussed before. But now, say you have a big supermarket, and you take a example of a city. You want to implement this social distancing uh, algorithm or the feature in your entire city. So there'll be thousands of cameras around, right? So you don't want you don't expect that one of the cameras feed has lost, and that camera's data you're not capturing. So in these 1,000 cameras, you want to make sure that you are getting consistent performance. But then you found that the bottleneck really is when I capture my data and store it in many memory. So that's in that case, if you see this kind of scenario, inline acceleration makes the sense because let's take an example of you have like say you upgrade your cameras to IP cameras. So the video data is coming through an IP channel, which is which is like say TCP or UDP protocol, and over Ethernet cable it comes to NVR, a network video recorder, and then from there you get it to your compute clusters. Now in this case, the FPGA will be receiving the camera feeds from the external world directly, not going through the processor. So that's where it's called inline. The reason is you're going to get the data inline directly to FPGA. In this case, there are two options. Either you implement the entire algorithm here, and if if the FPGA resources are enough, and you can implement all of them into this FPGA, you can actually process the entire thing and get back the results back to the world, that is the alarm and thing directly out without even talking to processor or without even bothering the processor in that case. So you get the camera data input to the FPGA, process it in FPGA altogether, and send the alarms back to the world, to the real world through to the same interface. Now, what is the role of processor? Processor will then configure the FPGA. So again, processor will be required, but will its main functionality is to configure the FPGA, saying what to do and what are basically to set the rules and to tell what exactly it should do once the data comes or how the alarms are set and all. So yeah, so we just saw what is in look aside and inline. So now we know now FPGAs are a good fit for as an accelerator. We know now they're very much interesting compute devices, and say you want to get it now. There are challenges, and traditionally, as an FPGA company, we have been solving challenges for user to make things simpler, starting from Cortex. Cortex is our compiler tool, which we discussed before. So Cortex, uh, to make it industry standard like an ASIC flow. So that was motivation. So we have been solving those challenges from long time for making the users more comfortable to use FPGAs. But then now in this evolving world, when we want people to use more FPGAs and to uh, make the FPGA as a choice for as an accelerator, we need to solve actually the problems which will be coming for the deployment of the accelerator functions. Now, what are those challenges? Basically, important from we'll go from left to right. So we see the board design and qualification. So you know that development of a board takes a lot of efforts, a lot of non-recurring engineering efforts are there. Then once the board is ready, a lot of qualification goes as simple as uh, your thermal aspects or your form factor aspects, your connectivity aspects like PCIe, memory. So making them all up is really a tough job, I would say, and we actually are making them easy. So we'll see how that. But important is board design and qualifications is something which we have taken care. Now software development, yes, this is again very important to look for for using any accelerator in a data center environment. We really need to have this FPGA seen from a software perspective as a just another device which is there in your system, like an integrated device. Like for example, as simple as today when you buy a laptop, you get your microphone, your camera, they're all inbuilt, and as part of the system, you don't need to you don't want to put your hands in installing all those drivers and all the softwares related to cameras. So similarly, when you buy a accelerator card, you don't want to really put your hands in building your drivers for it, or you don't want to waste time in doing all the setups, initial setup related to software. So that is all taken care. And FPGA accelerator development. Now we have hardware, we have software to use the FPGA, but then who will build accelerator? And if we have to build an accelerator, we need to have all those related IP cores, related uh, infrastructure, where easily anyone can just take that hardware and write their own code, which is accelerator function itself, not worry about anything else, and generate a bit file, the bit stream, and load it. So if you want to make this all thing happen, so it need to build an infrastructure for it. So that is also taken care. So we've been investing heavily on these three verticals and making it possible for our customers and for our partners to leverage our FPGAs for a data centric kind of applications. So we'll, of course, in next slide we'll be discussing about what are these boards, and in subsequent slides we'll be discussing what are the softwares and the infrastructure what I'm talking now. So these are few of the hardwares which we build, the boards which we build. Now, typically, I would say in day 7 and day 2, we saw the development kits, right? So we told that development kits are there for making your or doing a prototype, your proof of concept kind of thing. So, but then they're not suitable for production version because they have a lot of peripherals and being like they're made for doing your hand dirty, basically to get understanding of FPGA. But then in this case, these accelerator cards are really production worthy. That means you have to buy this FPGA and start using it, and they're all there. You can use it from day one. There's no need to do about any qualification or any uh, requirement for anything like does it's going to work for this temperature or something like that. So of course you need to take care of the specifications which is there in the document, but if you take care of all the specs, it's going to work out of box. Now these are the four cards which we have for different applications, starting from edge applications to network and communication to cloud and enterprise. So the first card, which is Mustang F100. So I'll not talk about much about that, and in this section because Vikas is going to cover that. So next is FPGA pack for networking. We call it as N3000. Again, N stands for networking. So these are used for networking and 5G kind of 5G deployments. We'll be talking that in a while. So, and then the next two cards, if you see the Ariadne GX based FPGA pack card. So pack is a programmable acceleration card. Programmable because they're FPGAs, acceleration because the functional is acceleration, and the card is because the form factor is a card. Just and they're all PCIe form factor pluggable. And on the right, we have a FPGA pack. D5000 is again data center, and it is based out of statics 10 FPGA. So you know that we have mid-range area 10 and statics high-end. So these two cards are for two different domains because of their capability in compute. So of course we'll be deep diving into it. We will actually see. I'll also talk about what is the specification of this FPGA, how you use this FPGAs and all. So let's get into it. But in meantime, let's first check what is our software portfolio, and because if you want to leverage the hardware, you need to start with the software. or tool developments, which is your EDA tools required for to program this kind of FPGAs. At the heart of the system, the software ecosystem, we have Quartus Prime software. Again, this is important to note here that it's the same thing. It is being covered in day two, and this is the same Quartus Prime software which you have used for multiple labs in this workshop. So on top of it, we have multiple flows which you can leverage to program the acceleration cards. Let's start from the top. So we have software programmers who can actually use OpenCL language and actually build uh, their algorithms into FPGA. Now they don't need to worry about any of RTL related syntax or even RTL language. They are traditionally software engineers, and we want them to use our FPGA. So we built software development kit for OpenCL, and which internally generates an RTL and generates a bit stream which can be programmed into FPGA. So this is all taken care by these two parts. As a software engineer, it is on a very high level. Next is an algorithm developer, like for example in 5G, say you want to build a baseband module, and in that you want to have an FFT, DFT, or IFFT, for example. So can actually build an algorithm. Yeah, like typically you need multiple points of FPGAs and different arrays, and you build those things there. And then MATLAB engineer doesn't need to worry about the RTL again, because DSP builder for FPGA takes care of it, and it generates an RTL internally, and then can actually even you can compare the and you can actually do simulations and compare what the outputs are obtained from MATLAB to the outputs of the simulation. So it's very seamless in the DSP builder. In the training page, in Altera or Intel training page, you can actually check. There are a good amount of training resources, training videos on DSP builder. I would recommend you to go and check that. Okay, so moving next, we have HLS compiler, which is targeted for embedded designer. So typically, embedded designers who write embedded C or C++. So, for example, let's take an example of SHA3 cryptographic engine, and you wrote a C code in for doing computing the cryptography. So you take that C code and give it to HLS compiler, and HLS compiler generates RTL, and that again you can verify using model sim, and then you can implement the hardware using Quartus Prime and then program the FPGA. So and traditionally the hardware engineers who use HDL coding, the QSys, that is platform designer, and again you take this RTL and then put it to Quartus. So this is exactly what we did in last couple of labs in this workshop. All right, so and then here as we show the gray lines, we can actually actually multiple people, like say software programmer, can still use HLS. Algorithm developer, when he develops something on, he or she develops some logic on MATLAB, can actually go to OpenCL and implement it. Or even if you say you have a CUDA code and say, okay, you want to have it come, you actually have, instead of using CUDA, you use OpenCL, like that. So just on a high level language, you can switch in between to any of this flow. So that concludes the first part, which is what are our acceleration solutions. So let's move to FPGA hardware accelerator for high performance computing workloads. So typically, uh, why do we need a why do we need a parallel computing is always a question, right? If CPUs are there and say CPUs were there from long time and lot of, like say we have multi cores now, we have 48 up to 48 cores uh, CPUs, then what is this need for having an accelerator as such? Because somewhere we're hitting power wall now, and that is because of the Denal scaling, that as in when we go to uh, uh, Denal scaling says that when you reduce the node, your process node, the chip manufacturing process node, the power also should reduce. But unfortunately, we have seen from a couple of generation in the technology node that the static power is dominating here, and we see a lot of power. In fact, the power is increasing now as compared to what it used to be decreasing compared to the process node scaling, right? So the question is, are we scaling the power? I don't think so. No. So the answer is like then split the computation into two parts. Why don't we split it like divide and conquer rule? You don't want to put everything in a single compute device or a single die. Rather, split the problem into two parts and then use it as and when I require. So and then the next is instruction level parallelism. So there are compilers. Basically, you have multiple pipelines, and then you basically so as a compiler, or if you see the compiler architecture, one of the major challenge I would say is how do you do a branch prediction, right? That's one of the challenge today in the software or in assembly language code uh, or a compiler design. That how do you jump or do a branch? There are of course branch prediction algorithm, but if you miss a branch, there's going to be a big penalty there, and you don't want to flush all the cache, and you don't want to flush out all the pipeline. So it's very expensive for us. So better we really build the pipeline and we implement the parallel logic into the FPGA kind of resources, right? So again, the memory wall. This is another interesting topic in itself. It's another research topic in itself. So we see that uh, the there are definitely bottlenecks in the memory hierarchies. So uh, in itself, even when we take on-chip bus connected to a memory, we do have limitations there. And if we take an off-chip memory, like say a DDR memory, the challenge is different altogether there. And that is where we have HBM memories. We have different memory architectures coming up, both in computers, in processor world as well as in acceleration world. For example, like Optane memory and all. But yeah, but here important is to understand there is definitely a crunch in bandwidth. Basically, you can build much faster instruction level pipeline or parallelism compared to the memory access bandwidth which we have, and we really don't want that to be a bottleneck for us and create limitations in our computing performance. Now, heterogeneous computing, we have been discussing this like because of our SOC devices are heterogeneous, as we said. Uh, so by definition, heterogeneous computing is a mixture of or mix and match of different computing devices. So so these are few of the computing devices which we have currently: CPU, DSP, GPU, and FPGA. And I just want to, okay, so these are traditional heterogeneous computing. But Of course, today we have ASICs also, which we discussed in previous slides. But typically, these are the heterogeneous computing. Now, we the thing is here important to understand is developing a custom uh, hardware or an accelerator itself, or a or a diff. Okay, let me step back and okay. So let's say we have all these four computing devices, right? So all these four computing devices requires different techniques to program, and that is where the challenge comes. Say you have a system with all these four different compute devices. For example, you might be writing C code in your for your CPU, and you'll compile it to your GCC, for example. Similarly, for DSPs, you will use say OpenGL kind of an application or an coding. For GPU, you may use CUDA or say OpenCL, and for FPGA, again you need to use RTL. Now, the problem is, how do you really make sense that in a very highly scalable, uh, high heterogeneous computing platform, that you are building this together to make sure that all the functionalities are working seamlessly? It becomes a challenge. So, we are trying to solve this problem by unifying this all together by our one API, which we discussed uh, in I think in day one and day two sessions. So one API helps to bring in the architectural platform, or you have software programmability independent of your architecture. So similarly, so in the same direction, FPGAs are also moving. So let's move to the next part. That is, let us see how our FPGA cards are getting enabled, and let's focus on this part today. How FPGAs are then being deployed in high performance computing. Where do you see this HPC workloads, and what all FPGA portfolios from Intel can help you to achieve those uh, HPC challenging uh, uh, or HPC challenging techniques, right? So for that we have hardware, as we discussed. We have acceleration cards for data center, and which is ARIA 10 based programmable acceleration card, and data center. Uh, uh, I'm sorry, for static 10 based acceleration card. So we'll look a little bit more details about what does ARIA 10 based pack card looks like. Uh, okay, so here we have okay. So this is how it will look like. It's PCA based PCA form factor card with 1.15 million logic elements, DDR4 memory. Again, two banks of 4 GB, so total 8 GB of memory. That's the off-chip memory. 53 megabits of data memory. That's the on-chip memory we call. And 1 cross 40 gig or 4 cross 10 gig of Ethernet capability. And on the left hand side, you see this port, which is the QSFP port. So this port, you can see it as an inline accelerator. You can use it for an inline accelerator. And attaches, and to attach this card to a CPU, you need some protocol, and we've chosen PCIe. So PCIe Gen 3 Cross 8, and important, any card. And when we say it's a production ready card, we need to make sure that this card doesn't fail. And in case if it fails for some reasons or any reason case, need to understand what is that reason. So to do debug that and to monitor the card, we have something called BMC. That's a board management controller. So that helps in about like programming the FPGA. It also helps to manage the temperature, voltages, and the form factor of this card is half length, half height. That means it fits in one single PCI slot. And also the good thing about this card, it goes in one RU. Basically, it goes in one RU rack, and the power consumption is 60 watt. That's the total I mean, it's a okay, sorry, 60 watts TDP with 45 watts on FPGA, and it is enabled with acceleration stack. Anyway, I'm going to cover the acceleration stack part. That's why I'm not touching it upon much at this level, but we'll see it in subsequent slides. Again, this is how it looks inside. By the way, it's like a high-level block diagram. You can say you get a QSFP plus with 40 gig of interface to the external world, and this is PCI form factor, which is powered by PCI powers, 12-volt power rail, and here, as I said, BMC board management controller is there. You have USB hub to upgrade the firmware because we have BMC uh, firmware to be upgraded, and you can actually store flash memory storing the FPGA bit stream, and a MAC ID PROM is required because you want to store your MAC ID if you are using a networking feature. Packard, again, we have another variant in Packard which is static 10 based. We call it as D5005. And so the ARIA 10 based card was 1.15 logic elements, while here it is 2.8 million logic elements. So almost you can say double of the logic elements. Again, 32 GB of DDR4, there 8 GB of DDR4, and magnitude increase in embedded memory, which is 229 megabits. Huge memory you get here, which is internal memory, and 2 cross 100 gig, 200 gig of you can get a bandwidth. Basically, you see the two QSFP ports on the left. We'll see the block diagram next. PCI Gen 3 cross 16, BMC, same BMC like what you saw in ARIA 10, and it's a 3/4 length and full height, and it's on a little higher power, that is 225 watts. But important to note here is you actually get 2.8 million logic elements with lot of DSP features. So the performance per watt is really significantly lower than uh, like say a GPU or any other accelerator. Yeah. So this is how this is a blow of the card. Again, two QSFP 28 gig, and you have static stand, SX, but SX, yeah. So you don't get an ARM core here. I mean, it's not enabled. And then Nperion is powered here. So, and then you have BMC and four DDR4 banks and a USB. So one of the important aspects about the acceleration in the data center is adoption by OEMs or server vendors, because uh, this card has to be deployed in the data center, and it has to go in a server, uh, a standard server chassis. So we have partnered with multiple our OEMs where we have tested cards on their multiple platforms like Dell R640, R70, and HP, for example, Proliant Gen 10, that is DL360 or 380. And there are many more actually, like Lenovo, and also we are still there are few OEMs who are actually doing qualifications, and there are few of them who are already done, and you can actually visit our Packard acceleration hub, and you can see what all those, what are the server vendors already supporting. Yeah, so the link for the acceleration hub will be given at the end of the slides. Yeah. So these are the workloads, and this is what I was explaining in the first section of my slides, that we do have examples of having acceleration workloads in data centers happening, and they're all happening, and they're all solving real world problems for your digital transformation. Like for example, you take from left, RENIAC is one of our partner. They have NoSQL and Cassandra database acceleration. That means RENIAC writes the code for in like they develop this acceleration function, and they provide it as a solution or an IP. And then as a customer, sorry, as a customer, you can actually, I'm sorry, our customer actually take these IPs and integrate to their softwares, and they are just replacement of the API calls, standard API calls required for database. So we have seen 6x performance increase with deterministic low latency, and that is where you get higher quality of service. And with this, what we saw was 80% of TCO savings. Now, what is TCO? Is the total cost of ownership. For example, let's take an example. You have a server and you're running, say, no SQL database, and okay, let's say you are building in your app, like say you're building education app, and where from that app you say you want to have your subscriber access to your videos, your classroom videos, for example, right? So you deploy all those classroom videos in your database, and of course you'll require username, passwords, all stored up in one database. And as an your subscriber base increases, so you'll see a lot of traffic coming to your server. Now, ideally, as a network infrastructure, if I was a network engineer, what I would have done is I would have, okay, I would have seen, okay, a lot of traffic is coming to my server, and there are few servers, or there are few requests which are not being served. So what I would have done is, typically, I would have put another server, and I would have split this database into two parts, and I would have managed this with a single gateway, saying, okay, half of your traffic goes to one server, half of traffic goes to server. But then say again your subscriber base increased, then what you do, then you put another service on adding the service. Traditionally this was done, but then with the help of FPGAs, what you can do is you can actually keep the same server, provided that there is no problem in rest of your application, and it's all working fine with that number of hits coming in. And you say there's some problem happening in your database, so you have an acceleration card, have a database acceleration workload, say for example, RENIAC, or you can build it on your own and put it in your and offload this database acceleration to the card. And maybe I would say you don't require another server to enhance or to handle the increased traffic. Again, as I said, it is again subject to your profiling and understanding your traffic, but still, this is how we calculated the TCO. Basically, typically without FPGA, I would have required for this amount of traffic, I would have required this many of servers. Now, if I have to manage the same traffic, I would still keep the server and add an FPGA, and significantly I would reduce the cost by not putting. That's the idea of TCO. And you would see across all our partners who have built solution on top of FPGA, they have they have got significant improvement in the TCO savings. So that is that was my motivation to explain the TCO here, right? And then SOM 64 again, we have a partner who is having an IP or acceleration engine for data warehousing. That is your uh, this is for data analytics part. And as I said, for scientific computation, genomics is okay. In healthcare domain specifically, again, scientific is a very broad uh, domain. In that, again, let's say genomics. We'll take an example in healthcare. That is playing critical role today. A lot of universities are partnered with us to have this solution. So the again we've got 5x of performance and 60% of reduced TCO with help of FPGA card deployed to perform genomics acceleration. Like to give few numbers, I would say that there again white papers are there. You just have to search it on the internet. But if I remember, uh, we like for example in the previous generation of our CPUs, Xeon CPUs, just CPU alone used to take, say, 36 hours to do a full genome sequencing. That is the WGS, whole genome sequencing. While, say, with FPGA, we have seen that has been significantly reduced to 3 hours, so which is like phenomenal, right? From 36 hours, we have just seen to 3 hours. But again, I would encourage you to go and again check the white paper. But why? The reason is again we have SSDs also. We have different obtained memories altogether. The solution comes down to 3 hours. So that's but one of the area of or one of the algorithms which is accelerated in this case is pair HMM uh, algorithm, which we implemented in FPGA and was accelerated. And the similarly, moving next, we have like another partner, CTXL, where we have this JPEG to Limpton and JPEG to WebP conversion. Basically, these are required for all your online web services, or the image is required for web services, like for example, Facebook or Google, for example. So the image is stored. So there are a lot of image conversion happening because you don't want to store heavy JPEG files in your server. So the compression techniques are used there. And this is a transcoding, image transcoding example where we saw 3 to 4x of performance. Make computing is another interesting solution partner of ours, and they have been implementing streaming analytics with the help of Apache Spark, Kafka, for example. So they have been implementing entire pipeline into FPGA, including the big deal that is a deep learning acceleration suite from Intel that have been also implemented into FPGA. They take advantage of our inline acceleration feature from FPGAs, and they get the data feed from directly from outside world into the FPGA. They do the image decoding or video decoding like H.264. Then they take the video, they rescale the video, and then they do the deep learning, and then they integrate it to the uh, Apache Spark framework. So as an Apache Spark user or a software developer who's building big data analytics frameworks, but they really don't need to worry about all this FPGA related stuff. They can just call an API where, like for example, RDD. So you just call an RDD and you get the stream out of that card directly to your application layer. You don't need to really worry about what's happening below. So that way, my computing is one of the example who is plug and play. You just have to buy, say, FPGA, buy an IP from Mac Computing, put it together, and install it, and you just get started with developing your big data analytics. and you focus more on your problem than managing the data itself, right? So next is Manjira Digital System. Again, uh, uh, they have AI engines, AI and RNN engines, basically implementing multiple workloads for again deep learning, machine learning kind of algorithms. So they have done a good job, and in the area of speech to text recognition, like for example Mozilla Firefox deep learning suite. So they have shown us a significant increase in implementing uh, those algorithms, speech to text algorithms into FPGA very efficiently, like 20x of reduced latency, right?
Ritesh,
And
just to interrupt here, I think there was a question on what is the kind of performance gain you can get on FPGAs. Probably Manjira, I think the answer to that question would be 20x for this particular Manjira solution. So you can think of, but the question did not have specific details, so we'll not be able to give specific information. But this is like a an indication. Thanks, Ritesh. Go ahead.
sure. Thanks, Vikas. And I would encourage participants to visit our acceleration hub. Again, the link to the acceleration hub is there in the slide at the end of the slide. So I would encourage to go to our acceleration hub, and in our partners solution partner page, we do have white papers and solution brief for all of them. So details of their implementation, their benchmark numbers, how exactly they were able to achieve. So all those details are provided in that, right? So and another is next is important part is our security. As I emphasized before, security is important and it plays a significant role in our today's digital age. Our data is important, uh, and protecting anyone, and in fact from any company perspective, right, protecting customer data is more critical today, right? It is as good as you providing what kind of services you provide to customers. So their FPGA has provided a good amount of performance boost, I would say. In another way that, say, if you have FPGA, the chances of getting a frame drops are less. In case of, say, deep packet inspection, we're able to get 40 Gbps without any drop in packets. You know, like as compared to, say, for I would have got some 15 Gbps with a normal network interface card. So that's the comparison: 15 Gbps versus 40 Gbps. And again, so more details are there on the NAPA white paper also. Okay, so in the HPC world, and then little bit uh, crossing into the cloud, I would like to bring in attention to Microsoft Project Brainwave. This is the link where I would encourage participants to actually go and, I mean, to read the research, where it gives a good perspective of how FPGAs are today used in data center, in cloud specifically, and how heterogeneous computing is used today. And if you do Bing search, that you're all traffic, or your Bing search when you do is hitting the FPGA in a way. So already FPGA is there in data center, and it's there in Azure cloud too. So on the right hand side, if you see, I just want to highlight the significant performance what we got from the FPGA. For example, Bing search, and with that Bing search, you do if you have a CPU only, the latency was like, say, 9 millisecond, while with FPGA, we got 0.850 milliseconds. So that's a significant reduction in latency, and that is where advantage of having FPGA into the system is important. Gives you a perspective of FPGAs are playing a major role, right? And on the left hand side is an actually how Microsoft data center are leveraging FPGAs to manage their data center, and how they are splitting their traffic across basically in their they call it as hardware acceleration plane, where the FPGAs are used to route the traffic like in a traditional NIC card versus the FPGA card here. So which is by the way attached to the CPU. Now let's look into the FPGA acceleration for networking part, because we're talking about 5G, and I touched upon how it's helping our telecom uh, customers, or how a telecom domain is being revolutionized, or I would say is getting disrupted with 5G technology, and how we are helping them to cope up that. For example, let's see again in case of network computation, right? How FPGAs help. Again, this helps is similar to what we discussed in inline processing, but this gives you a visual perspective. Okay, and it also actually tells you what is TCO saving. That's exactly what I wanted to. Uh, uh, this is exactly what I told when I was explaining you TCO, total cost of ownership uh, concept. Okay, for example, in traditional, you would have 56 core server, uh, just an example, right? And then you would have got a standard NIC. Now, this standard NIC is like this is which actually comes by default with your server. Now, what you do is your network function or your network capability on your standard NIC is up to only MAC CRC offloading. For example, you can actually offload MAC CRC here, and this more traditionally or mostly it is used as an PHY, because it actually takes care of converting electrical to optical and vice versa, and building a frame and then sending it over to the wire basically. So standard card, you just see it as a file layer. And of course, currently we have a Mac offloading also, but let's see, okay. And then on top of it, if you want to use a network functionality, like for example, in Ubuntu, you do IF config or IP config. So you see that you see network ports, right? So these network ports are these exactly these two ports which are coming, for example. And then uh, if you want to do some say ping you want to do, or you want to transfer some data from this port, you'd be using a TCP/IP stack ideally. It's a networking stack from Linux. So that actually runs on few of the cores actually. And say you're running say 40 gig of traffic, so 40 gig requires so many cores. So typically you would say 10 cores are getting consumed by doing TCP/IP offloading or TCP/IP work. Now, what if I offload this TCP/IP functionality and MAC offloading to the FPGA? I would probably save this course to something else actually, right? So all my cores are now being freed up to use and make use of something else. So directly your application can actually use FPGA as a card and do data transfer directly to the card. And it can see the network again, it can see the same network port what it used to be seen here. So the functionality is similar, but you offload more things into the FPGA than what is being done traditionally into the CPU. And with that, you actually get more cores here, and probably you will not require another server when your traffic increases, right? So that was the idea of total cost of ownership. And for service providers, so basically this kind of setup which is there with CPU and this network port this is all typically there um, in your data center, or if for service provider it is in your backend backhaul systems, right? So that in that case, with using this N3000 card, they can actually leverage more cores and reduce their cost. Now, this is a specification of PAC N3000. So again, it is based out of ARIA 10, so it is 1.15 million logic elements. So and it has a dual NIC card. This is very interesting stuff because this is something which takes me or differentiates this card from my pack card, which is the data center pack cards, which we saw before. Because that card did not have this chip, but this has an XL7110 Ethernet controller, which is in the chip. So with this enables to have the network port and implement all the network related stuffs here, and which enables your DPDK, which is our famous open source Ethernet drivers to be integrated to this chip. And we have 9 GB of DDR4 memory and 144 MB of QDR4 memory. So a lot of offloading can be done here. Plus 53 MB of embedded. And so we have enhanced our Ethernet port also. We have 8 cross 10 gig or 4 cross 25 gig QSFP ports. And then PCIe Gen 3 cross 8. And BMC, against the same BMC for this also, this is board management controller. And this is half length, full height PCI card. And this is slightly little power than the ARIA 10 card, which we saw for data center, which was 60 watt. Here it is 100 watts. The reason is because we have multiple peripherals like QDR uh, and the Ethernet controller. So obvious, and then the Ethernet ports are also more. So obviously the total power of the card itself increased. And as I said, it supports DPDK, which actually makes a very uh, convenient for any networking guy to use this card as an plug-in card. Don't need to do anything. You just have to plug card, uh, flash the binaries, and install DPDK driver, and you're straight away ready to ping from this card. That's required. That's the only required things to get this card up, right? Now, this is on the right hand side. If you see, you can actually have multiple workloads, and which we, I mean, these are tested workloads on this card like VBNG, IPsec, and VPC. We'll talk about that in next slides. So, if this card is for specifically for communications and network function virtualization, typically in say uh, in 5G kind of environment, we have so in 5G, we have in the baseband unit, this card is being used, and you would have heard about VRAN, which is Virtual Radio Access Network. From Intel, we call it as FlexRAN, and as part of the FlexRAN solution, we have Intel FPGA card, which is N3000 card used for accelerating which is LTPC is again your CRC for the 5G 3GPP standard, and few of the other workloads for the 5G baseband transmitter and receiver, right? So yeah, so again, telecom customers are using this for VBNG, which has quality of service. They implement quality of service into this FPGA classification, policing, scheduling. So basically, just to put it in a very high level, I would say suppose a network provider is there, your ISP is there, internet service provider, and based on your subscription, they need to manage your bandwidth, right? So there are different subscription plans from every vendor. So say you choose one plan. So based on your plan, they need to set up how much bandwidth you need, and they need to set up how much of data you consume, how much they have to make it something like FUP. They have to set up those rules, and those rules are done as part of they call it as BNG, and so, as part of that, most of the parts are now implemented in FPGA, and they're basically offloaded to this card so that CPU does more things than what you used to be done before. And then other standards like IP security, VPC, all those things are there. And of course, we have a lot of custom third-party partners who are also building this, and multiple workloads or multiple acceleration functions are being developed by our third party also. Uh, and that can be seen in your in the Intel FPGA Acceleration Hub. I mean, what all partners are there, which are FPGA boards are there, what solutions does the partner support to download a white paper. So all those things are there as part of our Intel FPGA Acceleration Hub. And then we can actually check out 01.org, which is our open source. Basically, DPDK is hosted over there. So the latest DPDK drivers are available from there. And yeah, so we're going to go next into acceleration stack, and that also is downloadable from Acceleration Hub. So we'll be moving further. That's our OpenCL flow, right? So on the we'll be talking about the high level software programming now in a couple of slides. So Vikas, we can take few questions, or we can take a.
No, I don't think there are any questions as such. I mean,
Okay.
most of them are already answered. So
Yeah. So I think I need to a little bit hurry now because yeah, I think we need to take a break at 12 o'clock, and 12 to 12:30 will be a break, and we'll be coming back by 12:30 for Vikas session.
Yes, sir.
So sure. So we have now. Okay, we'll be covering the software part. Let's get started with that. So as I discussed on uh, the earlier slides, that OpenCL is there for algorithmic developers, software developer as such, who have been developing different algorithms on CPU using high-level programming languages like OpenCL, OpenGL, or CUDA kind of, and where they've been using it for deploying, say, for a high-performance computing kind of workloads, right? So, how do we enable them for FPGAs? That is the key question, right? So we've been doing this, and we've been successful in doing this from quite time, and that is the motivation of this slide. That there's a host program written in OpenCL, and similarly, a software engineer writes OpenCL kernels, which can be compiled by our compilers and generate a binary. And this is all seamless, done by the OpenCL SDK, software development kit, and the binary files are programmed using command line. So you don't need to really worry about those programming lines as a software developer. So all those things are taken care here. While as part of the SDK, we also provide OpenCL libraries because, say, as part of OpenCL libraries, we also provide the BSPs, board support package, which are required to access the DDR, the Ethernets, and the PCI. So the peripheral interfaces are required to be used by OpenCL, but then since they are very board specific, that is provided by OpenCL SDK. And suppose someone wants to develop their own board, you can actually develop your own BSP. So we do have a good resources or a user guide to explain to guide you through building your own BSPs also. So in a nutshell, SDK looks like uh, we have a compiler which compiles the OpenCL kernels. Now this compiler is matured now, where we have a lot of pragmas supported by OpenCL, supporting this for an optimized implementation of OpenCL, and then uh, seamlessly the OpenCL SDK supports Cortex Programmer in back. As a software engineer, you don't need to worry about that, and then it generates a bit file, right, or a binary file. Okay, and so here now the programming, we saw the flow, how these two together work, and you have this a user program running into talking to OpenCL runtime, and then the OpenCL runtime is talking to FPGA. Now, typically, so this is how it happens in external hold. But that's what we discussed or we saw in our ARM core SoCs, that we have embedded CPU, user program, and OpenCL runtime, which is talking to accelerator. So both these, I would say, flows are seamless. So similar to what you saw in SoC EDS, the concepts are same to what is happening in OpenCL SDK. So again, not to confuse, these are totally two different tools, but the flow is, I would say, kind of similar, where you have you don't need to worry what's going on in accelerator. You have a handoff file, so kind of. Now, this is a compiler, and like, okay, so what exactly does the compiler do? It might be a question, right? So, how does compiler know what all things I need to build it in the FPGA, and it has to understand the FPGA peripherals, right, or FPGA architecture. So the Intel FPGA OpenCL SDK takes care of building kernels into the FPGA using the FPGA architecture. So because we have on-chip memory, which is actually makes FPGA as a unique proposition for accelerators. So because we have embedded memories, OpenCL also leverages this and uses on-chip memory as a local memory, and your external memory DDR as a global memory. So from a programmer's perspective or a programming model as such, you have an you have a memory, which is, you have two types of memory. One is your local memory and one is global memory. And then your logic elements are used to implement the kernel pipeline. So these all details are all part of the OpenCL SDK flow. Now, yeah, so this is again we discussed that from FPGA, as an FPGA developer, traditionally you require to know RTL languages, right? So but RTL languages are tough, takes time. It takes time to write code. It takes time to debug. Debug is really hard, right? So what we have done is, so to increase the productivity, so we have extracted or we have leveraged C++ based languages to even program the FPGAs. Now, yeah, so this is something briefly we discussed in previous slide, that is OpenCL programming model, that is host plus accelerator. Now, what does this do? You build an OpenCL program running on host code, and you actually call APIs to access your FPGA resources or FPGA kernels. Now, in this case, the function, whatever you want to accelerate, are built into the FPGA using local memories and global memories. For example, you're doing an addition, right? You're just doing an addition of two numbers, two floating point numbers. So you have float A, float B, and which results you're taking in Y. So Y GID is equal to Y of GID is equal to A of GID plus B of GID, right? Now this you can actually implement this in FPGA. So the OpenCL SDK compiles this to use the to build an adder into the FPGA. And while on the host, you just need to have these three steps to call out this functionality in this FPGA. Of course, to manage this board, you need to have the handlers and all. That's a different thing. But to just compute, you need an idea like CLNQ, right? Buffer. That means you are writing the data, you're writing data to the global memory from where these compute kernels can pick up the memory data, which is the input data. Then you say NQ ND range, and you say you initiate the computation and you read the buffer. Basically, once the computation is done, you read the buffer from the memory. So this way, this is the simplest implementation which I have demonstrated, where OpenCell host code is written and OpenCell kernel implemented in FPGA to add two numbers are implemented in the FPGA. Now this is another thing. So like OpenCL host APIs is an important aspect where how do you really use OpenCL SDK efficiently using an API programming, right? Or API or interface level. So we do have wrappers like say cl.spp, which actually don't need to worry about all the calls which are being implemented. They're all taken care, like what you saw, buffer write, buffer read. So they're all part of it, and we provide a standard C header for including it in your OpenCL code. We also have OpenCL platform layers and runtime layers. These are very important to make sure that you're using FPGAs or FPGA hardware as such very seamlessly without worrying about how your FPGA is managed, how your memories are managed. As a software developer, you only worry about your programming model, while you don't really worry about your platform related activities. So that was our OpenCL SDK. Let's move to the acceleration stack as such. Because acceleration stack is important when you want to use uh, FPGA accelerators or FPGA accelerator cards in the data center. The OpenCL SDK thing to remember here is traditionally being used by even in a different high performance computing setup also. I mean, you don't need it to be only in data centers. It can be on your desktop machine. It can be on your lab machine, which is running CPU, a host x86 CPU plus a card inserted to it in the motherboard, right? So this is all, or your own custom card actually, not only required for pack cards. But now we'll little bit move further, and we'll be discussing now on the acceleration stack. Now, how we enable acceleration cards, programmable acceleration cards for software developers, for RTL developers to leverage our pack cards. So typically, we've been discussing this. So typically, this is the hardware, and this is the board which we saw before. It might be ARIA 10 or static 10. Then we have an FPGA, which is blue in color is shown here, and we have a function implemented something here. Now, this blue color is a BMC, basically signaling and management, because again and this is done by us. So the blue color, just remember blue color, Intel blue. So this blue color is provided by Intel. While the green color is acceleration function unit, because this can be changed. I mean, this is a color code. Remember, green is something which you can change, which a user can change it, which a software development can write that can use this part of the portion of the FPGA. Now, almost like 90% of the FPGA is used for acceleration. 8 to 10% I would say will be used by the blue color. So we don't take up your silicon much. Uh, so almost 90% of the silicon is available for you to develop your acceleration function. And this acceleration function can be either Intel provided function, or it can be third party provided, or any research project which you're doing. So it can be part of this, right? Then we have PCI interface connected to a host machine. Now, host machine, your server, typically, for example. Then let's see in a software perspective. Now, in software, you require a driver which is talking to the FPGA via PCI, because as simple as PCI drivers you require. For example, as simple as like kernel driver like LSPCA, you require a utility like LSPCA, which internally calls a PCI driver, which is from Linux, to check what all PCI devices are there in my system. I just given that example, but these drivers are actually provided by Intel. Again, you don't need to worry about it. And drivers are implemented by drivers are part of Open Programmable Acceleration Engine. So OPAE is part of our one.org project. This is again open source, and we have good documentation on this. All the API calls are there, so where you can actually try to access the hardware seamlessly without even worrying about what is the resources, how much of GB this FPGA has, and all those things. So drivers takes care of it. And then we have libraries. It can be our own libraries or it can be third-party libraries. For example, like Med Computing, I told, they have libraries for Apache Spark or Kafka. So it can be Med Computing library, for example. And then application, it can be your application or third-party application. Like for example, you're building big data analytics, so that's your application which calls libraries and library calls the drivers. Drivers accesses the FPGA. So this is the overview of stack, and that makes like on that level, any software engineers doesn't need to really worry about what's happening about in the below layers. This is more detail about provided as part of acceleration stack. For example, we discussed about our hardware portfolio, right? We have cards, we have FPGAs. Let's not discuss about it with previous section. Acceleration environment. This is provided by Intel. With as part of acceleration environment, we have OPE, Open Programmable Acceleration Engine. Then FIM, as we discussed, it has all the management, board management related APIs, like say monitoring the temperature of the board, monitoring the power of the board. They're all done by this. Then Intel developer tools, like we have Parallel Studio. Then Parallel Studio is basically used to check. It's like a profiler, or it also has a compiler. So you can use compiler to compile different like C language or different languages. Like I would say, Parallel Studio has a compiler which is optimized for or Intel CPUs, right? Like for example, you can leverage AVX 512 instructions, and you can actually implement your logic efficiently, and you can fine tune using these tools. I'll not go into detail in this, but today's focus is on more on Intel FPGA. So as part of the tools, we saw SDK. So SDK for OpenCL is part of this stack. So even if an application developer writes OpenCL code, he's still using internally OpenCL under the hood, and they don't need to worry about it. And OpenCL internally uses Cortex Prime. So again, it is hidden, so you don't need to worry about Cortex Prime as such. But yes, internally it is there. And then acceleration libraries, yes, as I discussed, like we have DPDK, zlib, and zlib for compression, and then third-party libraries from our partners, and industry standard frameworks like Cafe is used for AI, Kino, and GTK. So GTK is one of the thing which I was discussing for genomics. So GTK is your genomic acceleration toolkit. This is jointly developed by Intel and Broad Institute, and it is open source. And one of the part is accelerated in FPGA as well, right? So and then user applications like deep learning, networking, and genomics. So again, so these are all we discussed as part of our ecosystem partners, and you can actually also implement your applications, the custom application, whatever you want. Then the rack level solutions. Again, we have OpenStack, for example, where like what the data center typically does, right? So you go and subscribe to a say to a service from in on a cloud. So cloud vendor gives you an instance of their VM machine, and under the hood they have OpenStack where they actually they may have OpenStack and they may have their own implementation, but just for reference, they use OpenStack for managing their hardwares. Similarly, FPGA also can be used to manage, or FPGA can be managed using the OpenStack. Yeah, so a few of the advantages of OpenCL on acceleration stack. So basically, we saw the previous section of OpenCL SDK was actually focused on the independent OpenCL development on any custom platforms. In this section, we are talking about OpenCL on acceleration stack. So say you get this card and you take a server, a validated server and this card, and you want to implement OpenCL algorithms, you can still use this open acceleration stack, and which is by the way, part of our stack, and you don't need to worry install OpenCL SDK separately. So it's all taken care in the acceleration stack itself. And all the features of our OpenCL SDK, which we saw in previous slides, are supported in this OpenCL for acceleration stack flow. Yeah. So so this is a little bit graphical representation of what I discussed right now. OpenCL programming. So you have OpenCL SDK for OpenCL. I'm sorry, Intel FPGA SDK for OpenCL. We have host code, and we have OpenCL kernel. We can use OpenCL emulator to simulate or emulate these two codes together and check the functionality without having a hardware with you. Say you are testing your algorithm, you can do that testing or checking the functionality without even loading that implementation on the hardware. So this emulation runs on the x86 platform where you have installed your OpenCL stack. And software compiler and OpenCL compiler, they are run in parallel. So basically, this OpenCL compiler generates an AOCX file, which is used for programming. Like, say, we have seen SOF file for programming the FPGAs. Similarly, AOCX files are the extension of the OpenCL compiler. AOCX stands for Altera OpenCL compiler. So this compiler gets your output of this compiler is .aosx file, and that is loaded into the FPGA. So there's no SOF file generated for this, just for information. And this is another hardware software co-design methodology which can be implemented in this in acceleration stack, where we have OPE, where you can develop C language, develop your C application. You can use software compilers, and then you can compile it, and you can run it on the CPU. And while you can actually write the acceleration function in HDL, RTL, whatever, Verilog VHDL, do synthesis and get a bit stream and load it in the AFU, basically in your FPGA. When you load that FPGA, the AFU gets loaded, and you can run your C code in top of it using the FPGA as an accelerator card. Or alternatively, if you don't have a hardware with you right now, you can actually take this too and put it to our AFU accelerations environment, or I would say AFU simulation environment, which is ASC, where you can actually co-simulate your C code with your HDL language. So with this, you can accelerate your development of your AFU without having dependency on the hardware. Now, next is the RTL simulation. Now, again, as I discussed in the previous slide, so this AFU simulation, I just want to emphasize a little bit more on this because there might be challenge in accessing the hardware, but it doesn't stop you from implementing any logic which you want to implement. So you write in software, in C, and you compile it in software, but using OPE you compile it. But that if you can use AFU simulation environment, you can actually co-simulate with your RTL flow, just like using model sim. And without that's again, it uses seamlessly. You don't need to change any code into your software or RTL. It's just command line arguments which you need to do to run the simulation. Zero code changes required to simulate in the to simulate without having changes in the hardware, right? So that way, what makes is like this helps so that suppose you have implement or you have verified this in the ASE. Tomorrow you can use the same C code and same RTL code to implement in the FPGA real hardware. Yeah, so this is again ASE details. A little bit I'm going a little fast. So it is based on CCAP transactions. Again, there are trainings on CCAP. CCAP is a protocol implemented to talk your talk PCI protocol to your AFU. So it's an interface between PCI and your AFU, and it actually models the memory map. Say suppose you have a memory implemented in CPU and you want to emulate that on the FPGA. So that FPGA memories are mapped into the ASC, where you can actually in simulation you can see the same memories which are there in the FPGA. And then this is done through DPI, this direct programming interface, and it can be simulated through VCS or model sim. Again, there are limitations in ASC. It's not cycle accurate, so you cannot actually you cannot use it to measure the performance. Again, AFU runs in model sim, but you can actually go and you can dump the wave and you can check the latency, you can check the performance. That's something you need to do manually. But as such, on the top level, if you run the C code and if you're running the RTL in the model sim, it is just as simple as transaction levels. There's no, it's not a cycle accurate, and there is no cache simulator. So any cache implementations cannot be implemented. And yeah, so again, since it is simulation only, the same rule applies to any RTL development, right? So if you use a non-synthesizable constructs, you cannot really guarantee that it will be synthesized. Now, building a AFU. So I will be showing this quickly. That I'll be accessing a dev cloud now, and I'll be showing you how to access AFU and how to build a AFU. But again, building AFU takes time. I'm not going to take time in building because compilation takes a lot of time. So let's not go into it. But I'll use the binary files which are already built to show how it runs, right? So basically, to build a AFU, you just need to use a run.sh script. Oh, yeah, and there are okay. So for example, you go to OPE platform root hardware samples and hello AFU. So I'm going to take this hello AFU and I'll show you how the RTL code is structured. So if you structure the hardware RTL code in the way which is required, then you just have to run this script, which is run.ssh. I'm sorry, run.sh. Because your platform root is set, this is already there in your terminal. You don't need to set any path for it. And you can start compiling your design without even setting up the pin constraints. You don't need to do all those things you choose to do in GUI of the Cortex. It is just a compiling run. So once it starts compiling, and once it is done, it will give a message saying compilation completed. And if you go to your binary directory where you compile, you'll see a binary file called .gbs, and you can just load the .gbs file into FPGA and just check how it is performing. So to start with, you just have to check. You start with hello AFU example, which is already there as part of our acceleration stack installation directory, and you have to use a AFU developer guide to know more about the signalings, how to write a code to target the acceleration cards and all. Yeah. So these are the reference documentation. I'll hold on this, but I'll just show uh, you a quick demo of our acceleration card. So I'm going to use a mobile term, and I have set all my credentials. I'm just going to SSH to my terminal using a script. Okay, so once you go to again, development cloud is free for everyone to access. You just have to sign up, and I think details are there in the day one workshop, Larry's keynote. So where you go to dev cloud FPGAs and sign up, you'll get an email from our team with a credential, username, password, and the related stuffs. And you go to the GitHub, and you can actually, for example, this is our GitHub for FPGA Dev Cloud. and there are instructions for accessing the dev cloud here, which you need to just follow these steps. Basically, how uh, like how to download mobile extra and how to log in or all those things. All the details are there. I'm not going to take up this in this session now, but I will leave it once you get the credentials, you can get started with this. Yeah. So I just logged into one of the server. So I'll be logging into. So the architecture of this dev cloud is we have a gateway server where all the requests first go to the gateway server, and then from there, based on the resource available, it assigns a particular development node. So I'm going to log into the development node now, and it gives me an option what type of development node you need to access. Like say ARIA 10 Packard for compilation and programming, ARIA 10 Packard for one API and OpenVINO, Static Time Packard for compilation and programming, and in this again RTLFU, OpenCL both are supported, and only compilation command line only. So you just have to provide. I'll just go for ARIA 10 for now. ARIA 10 compilation and programming. And then it asks which version of the acceleration stack you want to use. I'll just say 1.2. And I'm here. So now my node now. So that is N137, I guess that's my node. But I don't need to worry about it because it automatically assigns. And the good thing is even though if it assigns any of our resources available, I think there are uh, I think some more than 20 Packards are there, for example. Then you don't, even though there are randomly assigned, still your data is there in your head node. Basically, I have copied all my files here, and I see still it's there, even though my node name changed. That's why I don't need to worry about my data. It's secured in my head node with my login credential where no one can access it. Only I can access them. But still, uh, based on the resource available in the dev cloud, I still get different hardwares. Even if I log into Static 10, I still get the same. My code is as it is. Again, I'll be sourcing this script to log in. I need to source my tools, basically all the Cortex Prime and all those details. So in this case, I'll use ARIA 10 Packard compilation for RTL and OpenCL, which is number 5. And this will set up my environment of my installation. So for you, all the installations are completed in this. No manual installations is required, but this script runs only the environment variables. Setting up the environmental variables is taken care here. So I just need to check whether my FPGA is there or not, right? In this server. So because I don't see it physically, I need to cross check whether I can see my FPGA device in my dev cloud. So I'll do LSPCI. This is a utility from Linux where you check what all what all PCI devices are attached to your root complex. So LSPCI pipe, I'll do a grep of with my name. My name is actually accelerator. I mean, you can find it in user guide what name we have given. Either we can give it using this number, which is I can grep using this number also 09C4 or accelerators. I give accelerators because this number changes for static 10. If I give accelerators, I can see multiple. Say one server has both array 10 and accelerator. I can actually see both of them. And this is my BDF, bus device function. So on this device BDF, my accelerator card is sitting. Now, few participants had a question about how do I see power. And specifically on this board, how do I see power? FPGA info. FPGA info is part of my OPE stack. So that is why I said in my previous slide that you don't need to worry about any board related management things. It is all taken care by OPE drivers. For example, I'll say FPGA info and power. In this case, I'll see what is my power consumption, that is total input power. So right now it is consuming 21 watts. So if I load my bit file and if I again run and if I load more heavy compute intensive task into it and I run again this script, I might see my total input power increase. And this is the board power, by the way, not only FPGA, it is a board which actually senses the current and the voltage of all the peripherals required. And you see a PCIe voltage is all okay, 12 volts, 1.74 amps. It's all good. Yeah. So and for now, I don't need to worry about QSFP because QSFP, there is a I2C interface connected to QSFP module where I read the temperature and my voltage of the QSFP power, right? So yeah, I'm not connected to Ethernet, so I don't need to worry about right now. But there are some settings required to be done to read QSFP power or QSFP voltage and current. Okay, now let me go to my Hello AFU. I'm just going to show, this is the directory. Okay, this is what I copied, by the way. Let me show. Okay, so let me show in the installation directory how it looks. So I'll go to dollar OPA root, OPA platform root. So in this, I see this is my installation directory. It is recommended not to go in this and change here anything, because if you change here, your installation directory gets broken. Your compilation not may happen properly. So if you see here, we have hardware, OpenCL, and software. So I'll go to hardware because I'm doing a RTL Hello AFU. Now I have here blue bitstream. The blue bitstream is the one which I showed before, the blue color, which you don't need to worry about it because it's all developed by Intel. It is to make sure that the FPGA runs properly, and this is the 10% thing which I was telling. The 10% resources are utilized by blue bitstream, and that is required to manage the FPGA ports or FPGA logic itself. So let's not go into it. I'll go to samples actually because I need to see what all samples does Intel provide to us to get started. So if I see there are multiple examples provided by this acceleration stack like DMA, few Ethernet, E2E 40, again Ethernet E2E E10. So that is this is 40 gig, this is 10 gig, 40 gig, and then this is interrupt AFU basically to how to get an PCI interrupt. This is native loopback. If you don't need an say Ethernet cable, say you don't have an Ethernet cable, you want to see a loopback internally, you can use this native loopback. And by the way, native loopback is also used to check the status of the FPGA peripherals. Like for example, it is a self test. You can use it as a self test for a board. So suppose you're doing any transaction on memory, say DDR4, and you don't get response, and you want to check, okay, whether my DDR memory is working in my board, or is it has got corrupted, or some hardware issue. You can just run this native loopback. I guess mode 3, if you run, it does a memory transaction, and it checks.
We are already 10 minutes past the cutoff time.
Sure, sure. So yeah, so I'll just quickly wrap up now. So this is the example design. So I'll just go back to my folder here. I'll go to Hello AFU, and so in bin folder we have a golden GBS file. GBS is a green bitstream. Just for your just to remember, green bitstream, the green color AFU which we showed in the slide. So that's why GBS, just for remembering purpose. Okay, so I'll just say FPGA conf. This is my again OPE utility to configure FPGA. I'll use -b, and I'll use 0x3b. So I mean 3b is my bus number, right? So I need to use, because there might be multiple FPGA connected to my host machine. So I need to tell which FPGA to program. I don't want wrong FPGA program, and so I'll configure this hello FPU GBS file. So once it is done, it will show yeah, so we're done. And then I'll go one step back. In my hello AFU folder, I have hardware and software. Hardware, I'm not going, I'll just show hardware, RTL. I have all the RTL files. My AFU.sv file is here. This is my top file where my code is written. I'll not go right now in this. And I'll go to software folder where my software C code is written. I'll just clean it here because compiling the software code is very easy. It doesn't take much time. I just cleaned it. I just have hellofu.c and a make file. I'll just make it here. I run a make file. That means my GCC compiler run, and I'll get a binary file hellofu, and I'll just run a hellofu code. That's all. So running test is a printf statement, and then I print a few registers here. AFU IDs. AFU ID is 128 bit, so I'm just printing 64 bit. Then I have few scratchpad registers. Just remember our ARM SoC lab on day 7. So the same kind of example is there here. We have some scratchpad registers in FPGA. So we are trying to access this FPGA. So by default, I'm reading 00 because on reset, I clean up my register. Then I write some value and again I read this value, right? So just trying to do some transaction from the host CPU to the FPGA and just check whether it is writing properly or not. So I write some data, I read some data, and I just compare. Okay, it's correct. And then I'm setting this register to 0, and again I'm checking it whether it is correct. Just make sure that it is written properly. And once I'm done, I'm just say my test is completed. My hello AFU world wrote correctly. So if there is any issue in the hardware, this code is not going to run. I know you're not going to get this results as good as your clock is not working and all and so forth. So that's all. That's from my side. That's how you can leverage our dev cloud to develop your AFUs and to develop your acceleration algorithms. Thanks for all your questions, wonderful questions, and thanks for being attentive and listening to my presentation. Thank you very much. We'll quickly take a break. I know I have infiltrated. I have taken up your lot of your break time because
Firozaji, what time do we
Yes, sir. Good
back?
afternoon, sir. Yeah. Yes, sir.
What time do we come back?
Sir, I think so. Half an hour. Should we join by 12:45?
Yeah. Okay. Fine.
Yeah, because we are having a window of another half an hour extra because the validatory session is from 3 o'clock. So, and the session will end by 2:30. So, if required, we can extend it by 10 minutes if required, sir.
No problem. I think we'll try to cover it up. No problem.
Okay, sure, sir, sure. Okay, thank you, Ritesh, sir. Dear participants, I request you all to please join us by 12:45. We will start with the next session. Thank you, Ritesh, sir.
thank you, Firozaji.
Yeah, good afternoon, Ritesh sir, Vikas sir. Can we start, sir?
Firoza ji, you'll have to give me access to share the content.
Yes, sir, I'm just giving you the access, sir. Sir, can you share the screen?
Yeah, let me try. So I'm sharing the screen. Just let me know once it's visible.
Yes, sir, it's visible, sir.
Okay, great. So can we start off?
Yes, sir, sure, sir. Thank you, sir. Yeah, please,
Okay.
sir.
So welcome all for the last day, last session, and post-lunch session. Probably the worst possible combination we can have, right? So I'll try to keep it short and sweet so that I don't put people to sleep, and we'll go slightly in a brisk pace. Okay. And one thing I would like to request is the first part of this presentation, like the first two sections of the slide deck, I will be talking about Intel technologies, not exactly only FPGA, but it will be general Intel technologies for OpenVINO, which is our smart video toolkit, or we also call it as a AI toolkit for building AI applications, right? So if you will try to answer as many questions as possible, but this is like more like a open community, and it's open to the it's all on open standards. So we do have a forum. OpenVINO has its own forum where you can post all your questions and try it when you go hands-on, right? This is basically a slide for the workshop, so we'll not be doing all these things. But I think for today's presentation, we will be doing a basic or end-to-end object detection. We'll just tell you how to do it, and I'll share some commands which all of these can be tried either hands-on or you can try it on the cloud, right? So these are some of the legal notices which I have to go through. Right. So I think all of us agree that AI is the big game changer today, right? I think we are seeing AI getting deployed everywhere, anywhere and everywhere. Right? It could be emergency response. When we say emergency response, what it exactly means is it could be a case where you detect a smoke, right? Smoke detection, fire detection. Then once you detect the fire, how do we inform the authorities and things like that? Then we have the energy sector where AI is predicting models of grid power utilization, then trying to prevent the downtime and things like that. Education, again, there are two ways. One is transforming the learning experience by trying to understand what students are, how the students are learning. AI is being used today to conduct examinations where the new way of conducting examination is not to have a set of questionnaire, but the questions keep changing based on the students' answers. So that's the evolving new technology. We also have ICT, which is communication technology inside the classroom, where cameras can detect whether cameras can take attendance. They can detect whether students are sleeping, they're attentive, how many questions they asked, and a lot of analytics on that, right? Cities, again, I think all of us know these are all security applications. It could be starting from a smart traffic management system where traffic violations are getting detected, tickets are generated online, things like that, to crime detection, and a lot of those aspects. Finance, these are extensively in the fraud detection and things like that. AI is almost everywhere, right? Health, again, cancer detection, COVID-19, I think all of us know, we don't have to tell about it. There are a lot of applications on AI, especially in the X-ray and all those things. Industrial, again, it could be fault detection, preventive maintenance, quality inspection, and things like that. Media,
I think everybody knows. I'll not stress upon that. Retail, there are a lot of retail applications where inventory management, then you have like, theft detection in terms of in a lot of retail stores, people try to, change the barcode. They try to take one product along with the other together such that only one product gets scanned and a lot of things like that. So there are a lot of retail applications and it's running to billions of dollars. There is an estimate that Walmart really loses probably $5 billion only because of theft, right? So smart homes, again, here security is one of the applications, electricity consumption, all these applications is using AI. And you can see the various cases of deployment, right? The deployment condition, for example, the deployment condition for emergency response is like an industrial condition. So the different kind of hardware. For energy, it's a different kind of hardware. For education, it's a different kind of hardware, right? For each of these use cases, there's a different kind of hardware required. We cannot have one set of hardware to do everything, right? So how do we take care of that? Now, video is, as you saw before, video is the major, we call it as the eye of IoT, right? There are tremendous applications for video, right? Now, there are like different streams like, advanced medical research, personalized healthcare, smart transportation. I mean, almost up to 11 billion in edge to cloud industry today. That's like pretty huge. That's a huge chunk, right? And most of it is untapped. And as students and as universities, we can think of addressing a lot of opportunities in these spaces because it's very easy to deploy. You can deploy it in your home, sitting at home, you can build solutions, and it becomes very easy. And that is where this particular piece of the presentation becomes very relevant, especially to the student community, because our OpenVINO toolkit, OpenVINO, right, is free of cost, can be downloaded and executed on normal computer to accelerated hardware, right? Okay, so deep learning has been around for a long time. I think everybody knows about it, right? But in 2009, a team of Stanford, I mean, researchers at Stanford discovered team of sorry about that. Stanford researcher discovered that cloud significantly accelerate the training of complex neural networks, right? So basically, we're not talking about the training aspect, right? Again, this led to different things like accuracy breakthroughs in both speech and image recognition, right? In both the cases, machines have demonstrated lower than human error rates under a lot of under certain conditions where let's say you're doing an image recognition, probably the machines are now almost on par or probably sometimes better than humans in recognizing the objects. Now once you start recognizing the object, you can think of like infinite number of use cases and think of so many things which can replace human intervention which is being used today, right? um, in fact, there's a prediction that the AI will be around $13 million in economic value by 2030, which means the floodgates for the AI applications are yet to open. But when it opens, it's going to be a huge opportunity. So that's where it becomes very relevant for the student community and the academia to start building expertise in this particular domain, which is AI. Right? So in order to achieve our vision of artificial intelligence, then we must address each phase of AI development cycle, right? Data scientists today are forced to spend unacceptable amount of time in pre-processing the data, right? Iterating on models and parameters. Now waiting for training to converge, which is compute bound, and experimenting with deployment models, right? Experimenting with deployment models is like too much labor intensive or compute intensive, right? So that is where we get the Intel distribution of OpenVINO. right? OpenVINO is an open standard, open visual inference neural network optimization, right? So this is where we, help in deployment from on the edge to the cloud. So just note these words. What I'm saying is on the edge to the cloud, which means you can deploy it on the edge on your PC and your camera all the way to the cloud and the data centers. So it's a one toolkit, right? So how do we really make this happen? Correct? Okay. So what is deep learning? And as you know, I think the majority boils down to only two things, right? One is training and the other is inference, right? We often refer to the process of training a deep neural network and the process of using the trained DNN as inference, right? Now, in the example shown, the job of the DNN is to be able to classify the input picture, right? Classify the input picture into like different forms, like a person or a bicycle or a dairy or something like that, right? Lots of labeled training data is passed through the network in a forward pass, and with each new piece, the training data, the network makes a prediction. With each new piece of the data, the network makes a prediction about the images. Okay, the DNN predicts that it could be a bicycle, and there will be a certain percentage of confidence for the network that okay, the probability of this being a cycle is like 80% or 90%, which we call it as accuracy, right? Now, what happens is like this is in the forward path, like in the backward pass, right? The error propagates back through the network, and the weights, that is the interconnections between the artificial neurons, are updated to account for the error, right? Once these updates have been made, uh, the next time the same image is passed into the DNN, will be more likely to predict that it's a bicycle. So it's like you first detect, there might be an error, you send back the error, you correct the network, and again you detect. So with this kind of application, we kind of improve the network over the period of time, right? When the training process has been completed, the DNN is making predictions with sufficient accuracy. Then the model weights are frozen, right? So then that is when you actually freeze the weights. So once you get the weights, then it is ready for deployment, right? The same type of operations that are done for training must also be done for inference, right? In fact, as we have explained, training involves inference. So you could certainly use the processor designed for training to do the inference, right? So if you're using a Xeon processor, you can use the same processor for doing inference, right? But then the use cases for training and inference are not the same, right? You're doing training in the server, that's perfect, right? But then can you use the same piece of hardware to do the inference also? Yes, we can use, but then is it optimal? No, right? Like, for example, inference could be run on the field. It could be run in the, like if you talk about autonomous driving, though the training happens in the server and the data centers, the inference has to happen within the car, right? Let's say we are trying to do an automated conveyor system or a line for production line. Then even though the training of identifying a bad product happens in the data center, the deployment will happen in the factory floor, right? So similarly, almost every application you can think of a deployment scenario which is not where you cannot really run a huge compute, right? So these the kind of challenges in deploying deep learning neural network, will identifying these challenges will kind of help us in choosing which kind of platform and hardware we need to use. So what we are trying to do here is, if we can we are trying to tell about the problems so that you can appreciate the solution better, right? So what are the unique inference needs? Trying to reiterate the same things again, because it's like pretty important, deploying deep learning networks from training environments, typically in data centers or server farms, to the real world production use cases has always been very challenging, because in a server world, it's very easy, right? You have abundance of compute, abundance of power, and you can just run any amount of compute in a server environment. But the same thing is not true when it comes down to boils down to the actual implementation of a solution, right? There is a significant gap in the performance, accuracy, and other parameters, right? Now, there is also a lot of integration challenges, right? Typically, the training of deep learning networks is performed in data centers, right? Now, there is a disconnect in the end-to-end development workflow, right? From a software perspective, there are various programming languages like third-party dependencies. You might have trained in Python, that you might be deploying it in an embedded scenario, right? A lot of things like that which keep changing, right? So there is need for a dedicated API-based need, like what we shown here. No one size fits all, right? We cannot have one piece of hardware or one set of hardware which can fit all the needs, right? So that is where Intel OpenVINO has come into picture, where it's an API based, we can call it kind of an SDK or toolkit, API based toolkit. With one tool you can address all the hardwares, right? So moving ahead. Now, AI compute considerations, right? How do you determine the right computing for your AI needs, right? Let's start with taking the cross section of your environment to determine and break down the AI and other workloads, right? So there is a requirement of there's a lot of requirement when you talk about AI. You go to any AI, let's say you go to any company or anyone who wants an AI solution to be deployed. First thing you would ask is, what is the security of the data, right? A person, let's say a face detection. The person who comes in, first thing will ask is, how secure will my data be stored, right? Then, and then the second thing is, okay, today you're giving me a solution for like 10 cameras. Tomorrow I might install another 10 cameras. So is your solution scalable, right? Then how many frames per second can your solution do, right? So these are like hundreds of requirements which come into the foray. What you have to do is you have to see what is your requirement for this particular solution. Now, these are all your consideration for building a solution, right? So before even starting a project, these are a lot of requirements which you need to ask yourself and then come out with a proper requirement, and then come out with a demand for it, see how prevalent AI is there in that particular environment, see how much of compute can be done in the CPU, whether you need an accelerator or not. If you need an accelerator, then what kind of accelerator do you need? So these are typical considerations where you start from workloads, you check the requirements of the thing, like, and then you do a scale demand scale, right? Just excuse me for a second. Right. So why Intel AI compute, right? So to get the most out of the CPU, okay, why Intel compute and why OpenVINO? So if you see, the Intel understands its hardware architecture the best, right? So the CPU is the foundation for AI. So it's important to get the most out of it, right? It's very important to get the most out of your CPU. Intel is the CPU provider, I think for ages now, right? And we have invested heavily these last few years in both software, on open source frameworks and hardware, like deep learning boost and other optimizations, to ensure that the software and the hardware work together in tandem to build an excellent optimized solution, right? Now, the next thing would be the AI workloads and use case requirements vary widely. So having compute choice is very important, right? So you need to have the choice of your hardware. You cannot say, oh, I've got a GPU and I'm going to use it everywhere. No, you cannot do that. You cannot say, I have a CPU and I'm going to use it everywhere. No, you cannot, right? So you need to have the right choice for the hardware, right? And Intel is investing heavily in all major categories of accelerators. We have our CPUs, which are getting optimized day in and day out for AI workloads. We have our FPGAs. I think we have been talking about FPGAs for quite some time now. We have been Intel has having its own FPGAs, which is again being optimized for AI. We have our own inbuilt GPUs, which can cater to AI workloads. We also have our own ASIC, which are the visual processing units, and the Nirvana, which are an ASIC for special purpose computes and AI workloads, right? So now we have the base CPU, we have the choice of hardware for you, right? Now, how do we simplify the development, right? So AI is very complex, right? How to make life easier? Intel helps you to reduce the moving parts by building an optimized AI platform, right? And OpenVINO is one such platform, right? It includes common software, analytics, AI, all which can be accessed through APIs, right? Finally, the last part would be, AI is constantly evolving, right? And for AI of today isn't going to look like what AI you think would be tomorrow. It's like whatever we had 1 year back is not the same as what we have today. For example, when we started, AlexNet was the thing, right? Then came GoogleNet, then came ResNets. Like it's evolving every day. So it's important to align um, with the needs of the industry, right? Which is changing every day. So that is where we also lead in terms of uh, how to what do you call basically we lead in the industry efforts to bring scalable and deployable AI solution to the industry. Right. So Intel distribution of OpenVINO. So what is this OpenVINO? Again, Open Visual Inference Neural Network Optimization. Right. Toolkit is a tool suite for high performance deep learning inference. Right. It enables high performing applications and algorithms to be deployed in the real world. Okay. In addition, the path to inferencing is simplified with the streamlined development flow. So the development flow is very easy. I think we'll discuss this going down in further slides. Write once, deploy anywhere. That's a CPU, GPU, FPGA, MOVDS. I think in the further slides we'll just really discuss how that is being done. Right? With compounding effect of both hardware and software improvements, exponential performance can be realized, right? Exponential improvement in performance, I would call it, right? Intel is continuously shipping new hardware with built-in agility to adopt AI and develop deep learning with scalable flexibility. So again, one piece is hardware, right? You can see that Xeon Silver was doing 1x probably. The OpenVINO release, like what we are trying to show here is how Intel is working behind the scenes to improve the performance of OpenVINO toolkit itself on the existing hardware. Like in 2018, the first release of OpenVINO, if we were able to achieve the 1x performance, the same on the 2019 release was able to do 2.1x. And again, with 2019 R3, within the 3 quarters, we are able to do some of the cases at 25x, which means you are this as a student community or as a academia, if you guys are you guys can concentrate only on working of the algorithm, right? Accuracy of an AI algorithm or different new algorithms. On the back end, Intel is working on making these run more optimized in a more optimized way, which means your performance is taken care by Intel if you are using this open tool, right? I would again try to reiterate here, open we know is absolutely free of cost. It can run on a simple CPU also. I would encourage everyone to just go and register yourself, download, and you can start building AI applications, right? So deploying deep learning solutions with Intel distribution of OpenVINO toolkit. Basically, these are the 3 major operations or stages, I would call it. You build, optimize, and deploy. So let's take the build aspect. I'm not going to get too much detail into it. Just one slide which says, our world-class software team is dedicated to helping developers work how they want without limitations, right? Nobody wants to say, oh, I want to use this particular flow and this particular programming language. No, we don't want to do that. You can go ahead, choose any language, any framework, and we support that, right? We are trying to make it vendor agnostic, right? If tomorrow you go to any industry or like the whole world is now moving to open source software, similarly, everybody is moving towards vendor agnostic hardware, right? Today, you don't want to be coding in one particular language and you don't want to get tied to one particular hardware vendor, right? So it's like, why do you want to tie yourself and when things are really evolving, right? So that is where we support all these frameworks and tools and softwares, right? So the next stage would be to optimize. So once you build your network with the existing frameworks like a Tensor, Caffe, Kali, ONNX, then the next stage would be to optimize your solution, right? So we'll see how to do that. Now, OpenVINO has like 2 major sections. One is called model optimizer and one is called inference engine. So what is a model optimizer, right? It's a Python-based tool to import trained models and convert them to intermediate representation, right? So what happens is when you run a model, when you take a trained model and run it through our toolkit, it first goes through a model optimizer and gets converted into a .xml and a .bin file, right? Basically, what it does is it optimizes the performance or space with conservative topology transformations and hardware agnostic optimizations. What does this actually mean, right? Nice jargons. Okay. And in a very simple terms, I'll tell you. Let's say you have a trained model and okay, you might require like n number of layers, n number of accuracy and a lot of layers, especially for training. But when you use the same trained network for inference, you may not really need all that. So what the model optimizer will do, it'll remove all those unwanted layers which are actually required for training but not for inference, right? And also Intel knows it's hardware best, right? So there will be a lot of math in this train model, which the model optimizer will try to combine and ensure that the output is much more optimized than the input math. Like if you, it's something like if you're talking about a plus b plus 2ab plus cab, it's going to remove all the unwanted math over there and boil it down to a very simple equation. And it also ensures that the accuracy is not lost in the process, which is important for any of the AI applications, right? So the next is the inference engine. I think inference engine will also discuss in detail, but it's a high level C, C++ and Python based, inference APIs. So you can get APIs where you take it and you can integrate with your application, right? Interface is implemented as dynamically loaded plugins, which is on the fly you can change what hardware you want to use, and delivers the best performance for each type without requiring users to implement and maintain the multiple code pathways. Right? Just give me a second. I think there's a lot of background noise. Yeah, I'm sorry about the background noise. Some things are beyond the control. Yeah. So how does what does an OpenVINO deep learning workbench look like, right? It's a web-based UI extension tool for OpenVINO toolkit, right? You can visualize the performance, see where are the bottlenecks, a lot of model analysis which can be done. It automates the analysis of optimal performance configurations in terms of what kind of streams, how many batches you can run, what is the latency, and all those things. You can experiment with int8 or Vinogard calibration. Vinogard calibration is something like it's a different way of doing a vector multiplication, right? Which is more optimal than a normal vector multiplication. Okay, provide accuracy information through accuracy checker, direct access to models from public set of open model zoo, right? So you can, what I would like to bring to attention here is, though we have a lot of models, tools, and all those things, we are trying to ensure that it is as open and as community based as possible. We are not trying to tie people into one piece of hardware and one programming language, which is today extensively used for AI. Right. The other good aspect about this is a deep learning streamer, where Intel distribution of OpenVINO toolkit has a deep learning streamer, and now it's the default for all the installation packages. GStreamer is default, right? Enables developers to create and deploy optimized media analytics, right, and optimal pipeline interoperability using the GStreamer multimedia framework. So you can always go, we have given links in the PPT. You can always go to these links and learn more about it, right? So I would like to, pause here and see if we can take any questions. Ritesh, is there any questions? So Firozi, any questions which I need to take right now?
Sir, actually, till now there is no questions that I can check.
Okay.
Yeah, there is no, yeah.
Okay, thank you.
And also, if it is there, if there is something, sir, I will give you. I will
Sure.
inform you.
Okay, sure. Right. So now going forward for the deploying. 1 hour. Okay. So, like I said, we have cross-platform flexibility for OpenVINO. You can deploy it in your Xeon Atom Core and Xeon processors. You can deploy it on our Iris GPU, right? And you can also deploy it on our Movidius, which is a VPU or a visual processing unit, which is an ASIC, or on our FPGAs. So you can see the plethora of hardware which is available for deploying a deep learning neural network. Also, it's like we have the policy of code once and use it in any of the hardware. So you don't have to code for different hardwares for differently for different hardwares. Right? So how does it really work? So so here is where you would be developing applications, right? This is typically where people start developing applications, and they use a inference engine common APIs. So these APIs remain common for all the hardware. How it is managed internally would be like a multi-device plugin. Like for example, if you want to use CPUs, then the MKL DNN plugin will be called in, and your application will be using the CPU. If you want to use GPU, then we have the CLDNN plugin, which will be calling the OpenCL library, and then it will be using the intrinsic GPU. Similarly, GNA plugin for our GNA IP. Then we have the MoviDS, which is I think extensively used today. For Myriad and MoviDS, we do have the HDDL plugins and MoviDS APIs, which will get called by your application. Right? And similarly, the same common APIs will call the FPGA plugin if there is an FPGA to be used. So now you can see the application really doesn't change. All you have to do is common API on an open toolkit. Okay, so what are the tools to speed up the test cycles and development, right? First, we have a post-training optimization, which will reduce the model size into lower precision data types like int8, right? Or FP16, FP11, things like that. Reduce the model size while also improving the latency. Now, what happens is there are a lot of use cases where, a 2% loss of accuracy may not be very significant. Let's say you're detecting a person and it's trained on a FP32, we can easily port it onto an int18 with a small loss of accuracy, but a tremendous improvement in performance. So that is where post-training optimization really comes into picture. So we do provide that. Then we have a model analyzer, provides theoretical data on models, computational complexity, and the number of neurons and things like that. Then we have a benchmark app, where you can measure the performance, get performance metrics per layer on overall basis. We have a deployment manager to generate an optimal minimized runtime package for development, right? And deploy with smaller footprint compared to the development package. So similarly, we have accuracy and model downloader. Model downloader for easy way of accessing number of public models, as well as pre-trained models by Intel. So we also have our own pre-trained models which you can download and use it to develop your solutions. Right. So for example, in computer vision, we do have our own open source pre-trained models like object detection, object recognition, license plate detection, image processing, human pose estimation. So all these models, trained models, are available, and you can just start downloading and using it straight away, right? Similarly, we have text detection, text recognition for speech, then a recommender for action recognition. So plenty of these things are already available. So all you have to go is go to the GitHub, OpenCV, Open Model Zoo. You can go there and you can download all these models and start using them. And we have over 50 models and samples for that, right? Like I said, in the beginning of the section, I talked about so many use cases into so many verticals, industrial verticals, smart classroom. So we have all those demo applications in the models, right? You have a demo application for smart classroom, which means you can download the demo application, build your own smart classroom, right? Multi-camera, multi-person detection, tracking, gaze estimation. We have a lot of these examples already put into the GitHub. You can just straight away start downloading and using it. Right. Again, if you want to test the hardware, you're always welcome. We have a dev cloud where you can request for access, register and request for access, and then you get access to the dev cloud where all the hardware will be installed for you. Like we have the MoviDS, we have the FPGA, we have the processor. So you can go to the dev cloud and start testing your models for performance on various hardware. I think in the morning we had a question about how the hardware, what the kind of performance improvement you can get. Probably, if any of you can go and try the dev cloud and see which hardware suits your application the best. Right. So it's like, summing up the three important aspects: build, optimize, and deploy. So build your model frameworks, Intel optimized models, then all these models can generate or will become the input to your model optimizer, which will be the IR file. Now, along with the model optimizer, we can also have open model zoo, which I just talked about, where you have more than 50 plus pre-trained models with existing IR files, which means you can just straight away take this. You don't really have to worry about building anything. Just take these trained models, use the inference engine, target your hardware, and start building your applications, right? And for the FPGA, I think we've been talking about for FPGA, we've been talking about so many input methods, right? Like RTL, OpenCL, HLS, DSP builder, and things like that, whatever Ritesh talked about in the morning. Now, Intel OpenVINO toolkit has made it all of them, I would say, immaterial, right? So Intel OpenVINO toolkit comes with a lot of bit streams for a lot of applications, which we'll discuss in the last section, right? So all you have to do is just download, flash the bit stream, and start using it. You really don't have to even worry about coding for a bit stream, right? But yeah, one thing I would like to iterate here is if you still want to do on your own, yeah, even that option is available. So you can build your own bit streams and make it work on an FPGA. So that option is still there. But if you want to just concentrate on the application, yeah, you don't have to build a bit stream for the FPGA. Right. So I would really skip this slide in the interest of time. Okay. So though OpenVINO provides, deep learning inference and traditional computer vision operations, another right, but another big bottleneck in many applications is codec processing, right? All this H.264, H.265, right? Encode for streaming out can be especially very expensive. Media SDK enables real-time hardware accelerated video encoding, right? Video encoding for then run video and image processing with outstanding performance. That's the media SDK, which is included in the OpenVINO toolkit, right? With Intel Media SDK, you can develop professional grade media and video applications for digital surveillance, retail, industrial, smart home, video conferencing. I mean, many other applications which you can think of for video, video applications, right? Now, integrated graphics. So we have a Gen 9 GPU now. Okay. Now, Intel core processors include hardware, which is like I said, integrated GPUs, and OpenVINO toolkit is now also optimized to use this GPU, which is inside the processor itself. Right. These are the GPU configurations. I would not really get into too much details of this, but these slides are available for you. You can always go back and take a look at it. What is the typical workflow for applying OpenVINO and in computer vision applications, right? So you can see this is a typical traffic video which is coming in. So first thing what you do is decode the video, which is done by Intel Media SDK working on a CPU or a GPU, right? Then we have the OpenVINO toolkit, which has the OpenCV library in it, does the pre-processing of the input image, that is pre-processing of the decoded image. Then comes the actual inference, right, which can work on CPU, GPU, FPGA, or VPU. VPU here is a visual processing unit and is called MOVIDS, is one of our VPUs, right? We also have different products where number of MOVIDS chips are combined into one PCI card. So we call it Myriad. So yeah, what I'm trying to tell you is one OpenVINO toolkit can start all the way from decoding your image to pre-processing to running the inference on various hardware, then the post-processing again using OpenCV library for encoding it back to a visual format, again and encoding using Media SDK on the CPU and GPU. So you have an input video and you have a output video which has a car being identified, and you can also have a number plate recognition of this car, the color of the car, and all these things with just one command after you download the OpenVINO toolkit. Like you download the OpenVINO toolkit, pass a video image, and you'll get this kind of an inference already out. You can do two things, right? You start building an application on top of this trained network, or you start training your own network. So here you started with a trained model to go with a inferred image, but on the other side you can also train a model and go all the way till here, right? So there are two ways of working with this. Okay, so getting started. Now I told you a lot about OpenVINO toolkit. Now getting started with the OpenVINO toolkit, right? First you qualify, use a trained model and check if the framework is supported, or take advantage of a pre-trained model which is already available in the Open Model Zoo, right? Then you download the Intel OpenVINO toolkit from Intel Developer Zone, and then we have a very comprehensive starter guide. Please go through that. Then you can prepare and understand the tool. Then you run it hands-on. I mean, why I'm just telling these things are, it's very, very simple to do. So all you have to do is just download like any other software and start using, right? Support, like I said, it's a purely community forum. We have a huge community now which is getting active in the OpenVINO space. So you can post your queries in the community forum. Your queries might already be answered there. So just search for answers, right? There are enough documentation and enough example designs. You can take that and start building your OpenVINO applications or AI applications, right? So jumpstart your learning today. Again, I'm reiterating, absolutely free, no cost involved at all. Just download the toolkit. It will work on your course. I mean, i3, i5, i7, Atom processor also. So it will work on any machine. Just start using it today, right? Access other Intel software tools, that can be help build your solution faster, like System Studio, Media SDK, Intel SDK for OpenCL, deep learning tools from Intel, and context sensing SDK. So you can whatever AI field you want to work at, we have a solution for it. So all you need to do is start working on it from today. So that just concludes the first part of the presentation, right? So now I'll quickly take you through, an simple example of end-to-end object detection. It will be on a slide. Why we went for a slide is that, because you can always try it out yourself. It's very straightforward and easy. Right. So let's just quickly see end-to-end object detection. Right. So legal notices again, I'm sorry. So if you remember the first slide I showed you, the whole workshop actually contains a lot of things. But today we'll just quickly talk about the basic end-to-end object detection example. Right. So what do we have? Traditional method is you take a pre-trained model, take a video image, you have a user application plus inference which runs, right? But with Intel distribution of OpenVINO toolkit, you take a pre-trained model, you take a video image, the pre-trained model is passed through the model optimizer to generate a .xml and .bin file, right? So please note here, this model optimizer is a one extra step which you have to do just to get a optimized model like XML or a bin file. Excuse me. Yeah. So what does the actual model optimizer do? Right. Model optimizer has two main purposes. Produce a valid intermediate representation. If this main conversion artifact is not valid, the inference engine cannot run. Right. So this has to be done. The primary responsibility of model optimizer is to produce two files. One is a bin and another is an XML file. Bin file and an XML file. Right. Now pre-trained model contains just give me a second. Yeah. So the these layers pre-trained models contain layers that are important for training, such as a dropout layer and all those things. These layers are like useless during these layers are actually useless during inference, and might increase the inference time. Like I said earlier, right, there are a lot of layers within the trained model which may not be really required. So model optimizers will remove these layers, right? If a group of layers can be represented as one mathematical operation and converted into a single layer, model optimizer will convert that into a single layer. Okay, the result is an intermediate representation that has fewer layers than the original model, right? This increases the inference time and makes it more optimized, right? To produce a valid intermediate representation, the model optimizer must be able to read the original model layers, handle their properties, and represent them in intermediate representation format while maintaining the validity of the resulting intermediate representation. Um, uh, okay, what does it, how do we put it in very simple terms, right? Okay, let me put it like this. Let's say you build a original trained model has got an image size of, let's say, 100 or 100 by 100. So you have to pass even those parameters of what is the scale, what is the size of the image, and everything to the model optimizer. Otherwise, it doesn't work, right? So all these inputs of the original trained model has to be given to the model optimizer so that you get the best optimized model, right? Model optimizer loads the model into memory, reads it, builds the internal representation of the model, optimizes it, and produces the uh, intermediate representation, right, which is the IR. Right. So, what does a model optimizer perform? Model optimizer, performs generic optimization, something like a node merging, horizontal fusion, batch normalization, right? So, and these are some of the precisions which are supported. Like CPU supports FP32, GPU also supports FP32. Then FP16 supported by GPU, which is recommended on a GPU, Myriad, and the FPGA. Now FPGA also supports FP11. We are also in the process of supporting Int8 on the FPGA. So you can see that various precisions are supported by various hardwares, and these are again based on the needs. So typically, one of the ways on which the model optimizer actually works, I think I've told a lot about how what optimization takes place. I think this slide clearly tells how it works, right? Many convolution neural networks, includes batch normalization and scale shift layers. For example, ResNet or Inception, all these models use batch normalization and scale shift that can be presented as a sequence of linear operations, right? Additions and multiplications per se. For example, scale shift layer can be presented as a multiplication add sequence, right? A mult add sequence, and these layers can be fused into previous convolution or a fully connected layers, except the case where convolution comes after the add operation, right? So you can see here pointer. Yeah, so we got the pointer back. Okay. So you can see here, right, a lot of scale and operations can be merged into one particular fully connected or a ReLU layer, and then you can see the amount of optimization which occurs, right? Batch normalization and scale shift decomposition, right? On the basically on this stage, the whole layer is decomposed into multiplication add sequence, and then a lot of operations are merged to get a finally optimized representation of the original trained model, right? So the model optimizer, it removes the batch normalization stage because it's not required for inference, maybe, right? recalculates the weights to include the operation, then merge the convolution and ReLU into one optimized kernel. So your original model was something like this: convolution, batch normalization, ReLU, and max pool. Then because these batch normalization was not required, it's been removed. And then the ReLU is merged with the convolution, and finally in the inference, this is what you need. So you can see how 4 stages has been reduced only to 2 stages, right? This is exactly what a model optimizer would do. And also in the background, ensure that the accuracy still remains the same, more or less, right? So I would like, okay. So what is the purpose of model cutting, right? Now here's an example which can do that. A model has pre or post processing parts that cannot be translated into existing IE layers, right? So model has a training part that is convenient to be kept in the model but not used during inference, right? So model is like, there are various ways and which model cutting may be required, right? Model is too complex, right? Contains too many unsupported operations that cannot be easily implemented as custom layers for inference, right? Like under all these conditions, there are a lot of cutoff parts of a model which will be done. Right? There are a lot of command line options for doing model optimization. Right? Of course, these things are very clearly mentioned in the user guide. You can try all these things by simple command line. What is the intermediate representation? Right? So you have a SqueezeNet Cafe model and a SqueezeNet prototext. Now, when this passes through the model optimizer, you get a SqueezeNet.bin and a .xml, and it would look something very, very similar to the what input you had given. Right? So you have a reverse representation, and this can be easily visualized. The model optimizer output can also be visualized as the layers in the tool. Right. So the next important aspect about the OpenVINO toolkit is inference engine. Right. So after you have successfully created an optimized model, right? Using a model optimizer, you can using the inference engine. Using the inference engine, the intermediate representation can be easily the inference engine basically calls the IR files for doing the inference, right? The inference engine is a C++ library with a set of, C++ classes that application developers use in their application to infer input images and get the result. The library provides you an API to read the IR. Like for example, if you remember the earlier slide where I said, MKLDNN library, FPGA plugin, then you have the CPU, GPU plugins. So different plugins will be called by the inference engine. The API of inference engine is the same for all supported devices, right? However, there might be still some specific hardware configuration of specific device tuning, okay? But still, you can use the same API for all default as the default for all targets. So, like I said, it's like one code written for all hardware. So, I think we already kind of discussed this. So I'm just saying if there's anything specific to be mentioned again. No, I don't think so. We already discussed the slide, so I'll just skip this for now. Yeah. So what is the typical workflow of applying inference engine in computer vision applications, right? So you create an IE inference engine instance, load the IE plugin, right? Then the plugin will really read the IR model, which is the .xml and the .bin file. It will set the target, which is the target CPU, GPU, FPGA, MOVDS, and things like that. Then the load the model plugin, right? So it will take the load the model plugin, and then allocate input and output blobs for that plugin. Read the data into the input blob, run the inference, and this is like a iterative process. It keeps reading the input data, run the inference, and take the next set of data. Right. So this is a typical workflow for computer vision applications. So what is the first stage? If you remember, I had just discussed, right? Media SDK will be doing the encoding, decoding, and then you will have inference running, and then you will have again encoding for the video, right? So the first stage is always a pre-processing. Most of the data storage for an image can be pixel oriented or planar oriented. So this pixel oriented would be something like this, or in a planar format, right? For images in pixel order, all channel values for each pixel are clustered and stored consecutively. Their layout again depends on the color, model, and downsampling scheme. Right? Post-processing, we have developers are responsible for parsing the inference output, which is pretty obvious, right? Many output formats are available. For example, simple classification like AlexNet, an array of float confidence scores, like I said, in the beginning, where probability, it's like, okay, you pass an image of a cycle, the inference neural network will say, okay, the probability of this being a cycle is like 80%, 60%, depending on what kind of data set you are given for the training and how well the network is trained, right? Now that particular confidence scores, on the number of elements and classes can be used as an output format, and based on that, actions can be taken in the application. SSD, again, many boxes with confidence scores, simple object detection. You would have seen a car with a box, right? So there you can have a label, then you can have what is within the particular frame, X-min, Y-min, and things like that. And you can develop a post-processed application. Right. This is typically how OpenVINO installation directory structure would look like. You have the bin, you have the documentation. Basically, the primary folder would be, when you install it on Ubuntu, it will be OPT, Intel, Computer Vision SDK. This is the primary folder. In that folder, you'll have documentation, docs, and then you can find inference engine and model optimizer documentation, of course, with other documentations as well. So for this is for basically further reading. I would really encourage all of you to just understand the model optimizer and the inference engine, and then you have built-in demos which you can use for making your own applications. You can follow the guidelines of the demo, right? So this is the next section, which would be very simple actually, right? Hardware heterogeneity. I think we have talked about hardware heterogeneity from the morning, right? So what are the kind of different hardwares and how one programming language can be used on different hardwares, right? Introducing the heterogeneous plugin. The heterogeneous plugin enables computing for right sorry about that. To utilize accelerators, power, and calculate heaviest part of the network on accelerator, and execute not supported layers on fallback devices like CPU. What does it exactly mean, right? Basically, a heterogeneous plugin, what it does is, let's say you have a big network, right? Some of the layers may not really run on all the hardware. Like, for example, there might be a layer which is more optimized on a CPU rather than running it on an accelerator like an FPGA or a MOBDS or things like that, right? So the heterogeneous plugin will ensure that among the network, the right layers will go into the right piece of hardware. Like for example, FPGAs are good in doing convolutions, then most of the convolutions will be sent to the FPGA. If a batch normalization is not supported in the FPGA, then that will be executed on the CPU. Now imagine the kind of partitioning this involves, right? If you have to do it yourself, then that's a tremendous effort to identify which piece of the code will run optimally on which piece of hardware and to code it accordingly such that it gets executed on the right piece of hardware. Now, a heterogeneous plugin will do everything for you with just a simple command line change, right? So that is the beauty of this plugin. Now, the execution through heterogeneous plugin can be divided into two independent steps, right? First, you're setting the affinity to layers, right? For example, binding them to devices in the inference engine itself, right? The other thing is loading a network to the heterogeneous plugin, splitting the network into parts and executing them through the plugin. So how does this actually work? Let me show that to you. Now, how do we apply device affinities to layers automatically using a fallback policy? So I told you, right? You don't have to do anything to use an FPGA, and practically it is zero work if you want to use it as is, right? Here, this command is basically to show you an object detection sample SSD, right? And -m is the option to give the XML path where you give the model XML. You remember the XML was generated when you took a trained model, passed it on to the model optimizer, and the XML got generated, right? You give that XML as an input, right? Then you give an image as an input. -i is the image. Then -d is telling the inference engine on which hardware it has to be executed, right? So here you can give either -d CPU, like this hetero FPGA is not there, or you can give heterogeneous plugin, right? Heterogeneity is what we talked about. So you give a hetero colon FPGA comma CPU, which means highest priority will be given to FPGA, and things which cannot be run or which is not optimally run on FPGA will fall back to the CPU, right? But all layers are executed and you don't have to worry which will be on CPU, which will be on FPGA. But of course, if you want to do a performance analysis, there are certain command line arguments available to see which is how the performance is, right? For example, -PC is a command line argument which you can give to see the performance analysis, right? So again, like I said, these are applying different affinities to the fallback policy. You have the inference engine dispatcher. So this is a command. I'll not really get too much into the commands, but if you go through the documentation, you will be very easily able to do, assigning different affinities to the different hardware and then executing the layers. Right. Similarly, these are all again setting the affinities manually. So these are all commands which I would encourage people to try. So that is why we have put it in the PPT. You can go back, try it, and then if you have any doubts, please reach out to us, or you can always. There's a big forum for this. You can reach out in the forum, right? But some of the topologies are not friendly to heterogeneous execution, and that is where these things actually come into picture, right? So this kind of concludes on the overall open Vino aspect of this particular session. So I can pause here for 5 minutes or 2 minutes to take any questions if there are there. Firoza ji, any questions?
Yeah, because we have one question.
Okay.
Okay, so what is purpose of horizontal fusion in model optimizer?
Horizontal fusion is basically for merging certain layers, as far as I remember. But as I said, I'm really not the subject matter expert for that. Either they'll have to reach out to the forum, or I think the best thing is to reach out to the forum.
Okay, sure. Other than that, yeah, so I have answered other questions, so not
Okay.
much.
Okay, so finally we have come to the last part of the presentation, which is FPGAs for AI. Why do we use FPGAs for AI, right? So what are the things we're going to cover? FPGA architecture. Of course, I'm going to skip a few of them because it's already covered in the morning. Then I'll just talk about the Intel FPGA deep learning acceleration suite, and then few hacks of using the OpenVINO toolkit. Right. Just a quick recap. What are the kind of families we have? We start with probably Cyclone 5, Cyclone 10, ARIA 10, Statix 10. All these FPGAs can be used for AI, and going forward, some of them, especially the Cyclone 10, ARIA 10, and Statix 10, will be open for OpenVINO. As of now, there are a few dedicated cards, but going forward, you can have your own custom cards which will work with OpenVINO and these FPGAs. So isn't that really cool, right? Where you can build your own AI accelerator using these FPGAs. And okay, sorry, I lose the pointer every now and then. Yeah. So I mean, don't you think it's like absolutely cool? You can build your own FPGA card, right? And FPGA solution using OpenVINO toolkit and our FPGAs, right? So that is the level of customization we are trying to give, and that is how easy we are trying to make it for everyone to use FPGAs for AI, right? So IEI Video Analytics Accelerator card. This is one of our FPGA cards. I think it's called Mustang. So this is one card which is available in the market today for AI applications. The bit streams for this particular card will be available in our OpenVINO toolkit. That means you just take the card, you will have all these GoogleNet, ResNet, VGG, Tiny YOLO, all those topologies. We have given bit streams with FP11 and FP16, both the precisions. So all you have to do is take this card, install it on the system, download the OpenVINO toolkit, install it, and then start working and building your application. So it's as simple as that. The card also comes with a 4 GB into 2 DDR memories, right? Half height, half length PCI card. So it just slots into any of the normal machines which you can get. So this is off the shelf, kind of an edge application. Edge as in, a server sitting on the edge or a tank sitting on the edge. That kind of an application, this can be used. Right? What are the other possibilities of FPGA? So like I said earlier, apart from the typical FPGA use cases where inference itself can be run on FPGA, here we are giving two more possibilities where you have a Movidius simple pen drive which can be bought off Amazon, right? Plugged into the USB port of our Cyclone 5 FPGA. I think we discussed a lot on day 7. Ritesh talked about HPS being used in the FPGA and things like that. So here you can think of running OpenVINO and neural computer stick on the HPS and then doing a lot of other processing on the FPGA. So this will be beautifully used in a embedded environment where low power applications. This Movidius is like a 1 or a 2 watt device. We have a Cyclone 5 which is like 5 watts or 10 watts. So with as minimal as 10 watts, you can have a beautiful embedded solution, AI solution built using a neural compute stick with our SoCs, right? Taking this solution slightly higher, you can have our ARIA 10 based card, SoC card with a PCI based myriad, which means your OpenVINO is running on the HPS, then you have a PCI based myriad, and then you can build this solution. Right. So these are various opportunities you have, right? Or various streams you can think of building an AI solution using an FPGA, right? So again, what are the machine learning problems we're trying to solve? There are many advantages, like using the FPGAs, right? When integrated into an Intel AI software solutions and platforms, FPGAs are very easy to use and deploy, like I just showed, right? Either you use it as a controller block, or you can use it as a AI inference block. You have like high level of customization available, right? FPGA custom hardware and IO flexibility, high on-chip throughput that can implement low latency data paths. Low latency data path, where is it used? Like for a typical example is autonomous driving, where you don't have time for a processor to come and do the inference, right? You need deterministic latency, which means within 3 milliseconds you need to have the output, otherwise you're going to hit someone, right? Similarly, it could be a robotic arm in a manufacturing unit where the latency has to be very precise, right? You cannot have a processor or a AI inference running in a cloud to come and command a robotic arm, correct? So there are a lot of such hardware applications, right? These two specific applications where you need very deterministic latency, right? And evolving standards will obviously give you a lot of flexibility in terms of, like when you use FPGAs, you get a lot of flexibility only because of the reconfigurable or hardware option, right, which you can't get in any of the ASICs or the GPUs, right? So what is the other things the FPGA can do, right? So when you're building a AI workload, your weights and biases are your bread and butter, correct? And these AI workloads, for example, if you're building an AI solution for a smart city, then what you effectively have is deployment which is running years together. Someone can simply hack into the system and steal the weights and biases, which means your actual intellectual property, which is the weights and biases, are up for grabs. You don't want that to be happening, right? So that's where the FPGAs come with a very unique value, where the whole communication between the DDR and the FPGA is encrypted. The CPU to DDR to FPGA is encrypted, and FPGAs decrypt the weights and biases which are stored in the DDR on the fly, right? So that's the beauty of the or possibility with an FPGA, which typically is very difficult with any other kind of piece of hardware. So we have addressed the low latency, low power, embedded, and now security. So many concerns getting addressed with one solution, which is an FPGA. Right? Now, pre-trained video analytics model, I told you, right? We have plenty of models available in the open model zoo. So here is the list of them. It's not limited to this, but there's a very most used list. Age, gender detection, face detection, person vehicle detection, license plate recognition, right? So n number of applications, and all these things can be used on FPGAs as well. Emotion recognition, right? Right. So I think the list is like endless. It keeps going on. Right? So FPGA, why is it really suitable? Like I'll just quickly touch upon this. I'll not really go into detail. It is a highly parallel architecture. I mean, parallelism is taken to the next level, right? Configurable DSP blocks with FP32, which can go up to 90 flops, teraflops of operations, right? Tightly coupled high bandwidth memory, which means because we have distributed bandwidth, and Static 10 has a inbuilt 16 GB memory as well, right? So this is like highly coupled bandwidth memory, which will be useful. Programmable data path and configurability. I think we've talked about this in the morning, so I'm going to skip this. Ritesh talked about in the morning about all these things, so I would really skip this. But one small thing I would like to add here is the DSP blocks, which will do the matrix multiplication and the addition vector add. is the primary block which will help us in accelerating the AI workloads, right? So I'd like to skip this as well because it's talked. Yeah, so this is an interesting piece, right? How is it that FPGAs can, or rather, how is it the FPGAs are very inherently parallel in nature, and how is it that we get a very optimized performance out of an FPGA, right? Uh, so here is an example of a high-level code where you have a basically multiplication and then you store it back into the memory. You do a multiplication and addition and store back into a memory. A typical operation, a very, very basic operation involved in almost all computations of AI, right? So how do we do this? So basically you can see the steps involved. First, load the memory into a register, load another data from the memory, right? Then you load the actual value or the operand, then you do a multiplication, then you do an addition, then you store it. So what is the hardware required to do this, right? So you can see that this is a typical hardware, and for this particular load operation, you can see that a fetch, it's going to decode the instruction, then it's going to store it, then you have an operation, and then the carry is stored. So this is a typical operation, which is in general very good, but in this particular case, it becomes an inefficient hardware, right? So if you analyze this in a time domain, you have this piece of repeating hardware which is doing all these operations, right, from the time domain. Right? You take this, you give, you take this, you give, you take this. It's like for every piece of operation, for example, in this load operation, the ALU is useless, but still being used, right? So in these three operations, the ALU is actually redundant. In these two operations, the registers are redundant. So in the last operation, again, the ALU is redundant, but still it's being used. And you can see that everything is in a time domain, which means it's getting executed sequentially, right? Now, what happens in an FPGA is this whole time domain operations or a sequential operation can be unrolled, and it can be made into a space domain operation, which means whatever is happening sequentially can now become space domain, which means we can remove all the redundancies for those particular operations. The load operation, you don't require an ALU, you remove it. So similarly, each operation can be optimized. So once this basic optimization is done, the next is we need only two registers. You don't even have to be loading, right? Because the data is always available in the FPGA then and there, right? So you don't need actually a load operation. So the register is always there. All you have to do is take the data with a multiplier and an adder and a register to store. And that's about it, right? So now you can see how we started from here as a CPU operation, went all the way to optimize to have such a small piece of hardware. So this is where, you know, Intel FPGAs can become highly parallel and highly optimized solution for AI workloads, right? So just to summarize, uh, advantages of Intel FPGAs on AI: custom hardware, efficient processing, fine-grained parallelism, like just now what I showed, low power. I just showed you how low power it is because all the redundancies are removed and this is customized hardware. Flexible. Today you want to do GoogleNet, tomorrow you want to do AlexNet, the day after tomorrow you want to do SqueezeNet. Everything is possible with customized, reconfigured hardware, right? Faster time to market, obviously, because you don't have to spend the time in making an ASIC, running through the long processes. Many IO standards, because like let's say camera standards are changing. Some are IP cameras, some are MIPI, some are H.264, some are like various cameras with various standards can be supported with one particular FPGA. So these are the advantages of using an FPGA in building an AI workload, right? So what is the typical what do you call machine learning workflow. So let's just quickly, do a recap on this, right? First, you decide on the network topologies then you decide on which algorithm like a ResNet, GoogleNet, framework is decided, Caffe, TensorFlow, like that. Then you decide the topology like a ResNet or a GoogleNet or a SqueezeNet. Then you train the network. Basically, you have a big set of data, store the data, then you train the network, right? And then deployment, right? Inference engine. And FPGA is the focus for this particular deployment. Please note, we are talking only about deployment and not training here. So our focus area for use of FPGA is inference only, right? Of course, then we have, you collect the more data and you improve the data set to get a better train network. Again, the process remains the same, right? Once you have a better train network, you pass it on. You remember our model optimizer, it goes through the .xml, .bin gets generated, and then the deployment happens on the FPGA, right? So how does it work internally? So this is like an overall picture where we started off with a Caffe tensor, kind of an MXNet model, goes to the model optimizer, IR, then you get the FPGA here, the inference engine, right? Now, what are the components within the toolkit which is enabling it, right? We have the traditional OpenCV, OpenVX, SDKs. Then I told you about the media SDK and OpenCL for GNA applications. Then we have something called the Intel FPGA Acceleration Suite, right? Here again, we have two things. One, runtime environment, wherein you can use the bit streams, or you can go for a developer environment where you have OpenCL SDK, and then you can take the DLA suite from Intel, and then you can start developing your own bit streams, right? So how does it actually work internally, right? Here are the features of the DLA, right? DLA suite, right? This allows you to take advantage of the FPGA without going through the lengthy process of traditional FPGA development. The DLA suite consists of various implementation of deep learning primitives, right? Organized on a crossbar, right? These deep learning primitives could be like a ReLU, MaxPool, and things like that, right? So to implement like different networks like an AlexNet or a GoogleNet and variety of other topologies, right? You don't really have to recompile on the FPGA, right? The DLA architectures, oops. Okay, sorry about that. So my laptop screen went blank for a second. Right. So the DLA architectures implement optimized common deep learning primitives such as convolutions, fully connected layers, rectified linear unit, which is a ReLU, local response normalization, max pool, all these things as primitives, right? You can also have your own custom primitive. Let's say tomorrow you do research and then you come out with your own primitive, then you can just simply add it here, right? And all these things will be configured using a config engine which is sitting within the FPGA and will be used by will be configured by the inference engine API, right? So the weights and biases actually come and sit in the DDR in the card, and the input data is continuously streamed into it with the inference running on it and then streamed out through the PCI. There are various pre-built images which are supported on the FPGA. Oops, sorry. Right. So yeah, so going forward, what exactly we'd like to reiterate here is we support common frameworks like Caffe, Tensor, and other things, right? the model optimizer in the DLDT or deep learning deployment toolkit will take the standard machine learning formats and converts it into Intel specific intermediate representation, right? This is what we've been discussing probably the last 1.5 hours. Right now, it comes to the MKLDNN, and the inside the FPGA is where you have these different bit streams for different topologies, which gets programmed onto the FPGA, and you can just start using that. All right. So these are the two typical flows where you have the application developer who design on the OpenAI toolkit, and you run it by programming the FPGA. So normal workflow is what is being explained over here. The other thing is you have an architect who really, customizes a DLA suite source code. Again, here the customization can be on two levels. One, you build your own, you do at an architecture stage customization, which means it will involve changing a few parameters, right? Or you change, you add your own layers and create your own custom model. That is also possible with an OpenCL SDK, and then build your own bit streams. Right? So we'll see how that really works. So this is one level of customization. Like I said, you can do at the architecture stage, right? So if you need to customize the FPGA architecture, DLA suite allows you to select the place of custom collection of pre-optimized primitives and convolution PE array onto the FPGA. Okay, if there are primitives that you need but are not supported in the DLA suite, for example, like an uncommon activation function, right? Then you can write a custom OpenCL code, okay, for those functions, and then add it to the DLA crossbar. Right aside, this is the second level of optimization. You can make your own models and then add it there, right? Okay, the DLA supports also 3 different types of custom primitives: the unary operations, like hyperbolic tan activation or the ReLU; the binary operations, like for example, element-wise add or multiplication. Also, and the Windows operations such as pooling and normalization and all those things. Right. We also support operations such as scale or dropout for coefficients, where coefficients are loaded into the on-chip memory through configuration registers, or for operations such as batch norm, where there are lots of coefficients per layer. They can be loaded from the off-chip memory. Right. So, I know there are a lot of terminologies here. It's very difficult to get everything in one shot. But the key takeaway from this slide, I would say, is if you are developing or researching on the AI, we do have all the options for you to deploy that on an FPGA, right? And to take your optimization to whatever level you want. So, how do we support different topologies, right? There is a trade-off, of course, right? Everything has its own cost. So if you have less primitives, then you have more space for the convolution array. So you have a better performance, which is shown on the left side, right? You have less number of primitives and you have a big convolution array, because FPGAs are very good in doing convolutions, right? The other option is you have a convolution P array, lesser one, with more primitives on the crossbar, which means you're doing more different type of layers, less convolutions. This also gets executed on an FPGA, but then the performance may not be as optimal as this. Another thing to note here is if you have layers which are not supported on the FPGA in your train model, and if it is such that the layer on the CPU and the layer on the FPGA are in tandem, which means there is a lot of to and fro between FPGA, CPU, CPU, FPGA, FPGA, CPU, like that through the PCIe, then also the performance may not be really optimal, which means while doing the analysis, you have to be very, very conversant of the fact that the layers on one particular piece of hardware should be as close as possible to each other, right? That way, you're avoiding a lot of to and fro transmission of data from CPU to memory to FPGA and things like that. Right. So another thing to keep in mind while choosing a network architecture for FPGA image is the data type. Right. For example, there are different data types: floating point 16, of FP11, FP10, and things like that. Right. One thing is you don't have to retrain the network. Right. Um, default DLA data types are all reduced to precision floating points ranging from 32 to FP8, right? When executing the reduced precision floating point numbers, FP16 or lower, the DLA will perform block normalization, meaning normalize the exponent for all value, and then instead of performing a floating point multiples, it will use fixed point multiples. Okay, but what I would like to bring to attention here is, if you have trained your network on FP32, then you really don't have to retrain it on FP16 or FP11. You can simply port it onto an FP16 and FP11, it will work, right? So that's like a lot of effort saved. But yeah, other thing is, when we reduce the accuracy here, one thing I would like to say is, when you reduce the precision, the accuracy will also drop. But like I said, there are a number of applications where small drop in the accuracy or the small loss in accuracy will still keep the performance the same, performance of the system same, right? Some of the supported primitives, I think the very small list, I think the list is really huge. Okay, so I would really encourage you to try these optimizations on our dev cloud, or you can have your own hardware in your lab and you can also try that out. So how do we install this? Please note, we have a separate Linux for FPGA download link for OpenVNOM. Right, there is a Windows version, there's a Linux version. Now we do have certain cases being supported on Windows as well, FPGA being supported on Windows as well. So please download the correct software if you want to do installation on your own, right? And automatically fallback option. I think we already discussed this with the hetero plugin. You give a hetero FPGA, CPU, right? Keeps all the layers that can be executed on the device that's on the FPGA, and basically takes all the layers which cannot be executed on an FPGA to the CPU. Right. So this is very key. Even by mistake, if you give hetero CPU, FPGA, then the priority goes to CPU. Even though everything will get executed, but the role of FPGA will become very minimal, which means you will not see a huge difference in the performance. So it's like, it's running, it's as good as running on the CPU if you put CPU first. So whatever comes first gets the highest priority. That is one thing to note over here. Right? I'm not sure if it is really clear, especially this thing. I'll read it out for you. Right? Basically, you have to prepare the environment for running inference on the FPGA, right? Which means basically you'll have to follow the user guide, that's for sure. Right? But you have to set the environment variables. You have to use the script, something, and set the LD library path for the OpenCL libraries. And once you do all that, if you type this command AOCL diagnose, I'm reading it out for you because it may not be very clear, but these slides are with you. You can always go through that again. Right? AOCL diagnose. Right? Once you do this AOCL diagnose, you will get the name of the card and it says diagnostic passed. This is the first step without which the FPGA will not work. Right? So once you do all the installation thoroughly, this is a must. You must get a diagnostic pass, which means the FPGA has been detected. Right? So once the FPGA is detected, you have to load the image, which means you have to program the bit stream. You have to choose the bit stream from the delay suite, and that depends on the topology. Right? I'll read this out again. AOCL program ACL 0 dollar $DLA AOCX. Okay. So if you go to, if I show you in the previous this thing, here you would get the name of the what do you call the card, ACL 0. So you can see here the ACL 0 is the name of the card. So in the next command I have given AOCL program ACL 0 dollar $DLA AOCX. Basically $DLA AOCX is nothing but the path where the actual bit stream is residing. That we usually map it. Otherwise you can give the absolute path. There's no problem. Right? So once you do that, it will run the programming and it will program the FPGA and you'll get programming succeed here. Right? There's a programming succeed which comes up. Once that is done, all you have to do is now run the application which says classification sample. So you just ran a image classification with the -D hetero FPGA CPU, right? So again, please note that whatever comes first has got highest priority. If you do a CPU first, then it will get executed on the CPU, right? In summary, FPGAs provide a flexible, deterministic, low latency, high throughput, and power efficient solution for accelerating AI applications. FPGA delay suite supports CNN inference on FPGAs. Right? This can be easily accessed through the OpenVINO toolkit and available for all Intel acceleration pack cards, whatever Ritesh talked about in the morning, right? The pack cards. So we do have bit streams even for those pack cards. And going forward, we will have option to build custom cards where you can build your own accelerator card, which can use OpenVINO toolkit. Right? So we've come to the end of the presentation. If there's any questions, we can take it now. Ritesh, do we have any questions?
Yeah, we have one question.
Okay.
But I think yeah. So give me a moment. Yeah, give me a moment.
Yeah, sure.
Okay, yeah. The question is, how does embedded UVM pass stimulus to FPGA on SoC FPGA? I guess this is Punit's answer. I mean, he can answer this question.
Yeah.
Yeah, this was one of the multiple choice questions, and the answer is using the programmable part and the HPS and programmable logic interface. So yeah, using the Avalon bus, and Avalon bus is using that interface. So that's it. So probably the person who asked the question, he needs more understanding of the concept, like how the interface works or how it is used. So that's why he is asking.
Okay, so right, so on the bridge side, yes, as we discussed on day 7, from HPS to FPGA, there is a AXI bridge. Again, there are 3 bridges which are available. One is the high speed HP to FPGA. Second is lightweight HPS to FPGA, and third is FPGA to HPS. So this FPGA to HPS is again a high bandwidth. So so this is the bridge which is to pass any data from FPGA to HPS or HPS to FPGA. Yeah, and a little bit the options were like Ethernet or PCI. These are actually external interfaces. So these interfaces are used for data transfer to the outside world. Say Ethernet is going on the Ethernet cable, while PCI is going to your host subsystem, where a card is connected to a host motherboard. So, because I think all other questions I have answered, and I think we don't have any questions other than this.
Okay, fine. Okay, I think, okay, these are all multiple choice questions. Okay, okay. So that has come back. Okay, fine. So it's not related to today's thing. Okay, fine. Okay, I think if there are no further questions, Firoza ji, over to you.
Thank you, sir. So, Puneet sir, can I request you to please answer to few of the queries which are related to the yesterday's MCQ that we have given to the participant? So,
All right. So
yeah,
if you can pass those on to me, I can do that right
sure.
away.
Yeah,
Or
yes, sir.
yeah.
So, just 1 minute, sir. I'm just giving you the privilege. Thank you, Vikas sir. Ritesh sir, we will be having the validatory session from 3 p.m. So, sir, please be connected with us.
Yeah, sure. And thanks a lot for all the organizers. It's been a great event.
Thank you, sir. Puneet sir, can you please check we have given you the privilege?
Yeah, but I need to know the question, like which question to answer.
Sir, actually, sir, in the question answer section, there is one multiple choice question is given, like how does the embedded UVM passes the stimulus to the FPGA on an SoC C FPGA?
Yeah. So
Sir,
Ritesh just handled that question just a minute back. So that's answered.
okay, and I think so. There were one. Okay, sir. No, I think so. That was there. Yeah, I think almost. Okay. Yes, sir. That has already been answered. So, sir, I think there is no more question answers. So, can we break, sir, for half an hour, and we will be connecting back again at 3 p.m.
Okay, as for the code I used in the sessions, I'm in the process of, because I need to clean them up a little bit. So I'm in the process of uploading them on GitHub. I'll be doing that
Okay,
during the
sir.
weekend. Okay.
Okay, sure, sir, sure, sir. Thank you, sir. And dear participant, we will be sharing one link to all the respective coordinators. The coordinators will be sharing that link to all the participants. So I request you all to please be connected with the WhatsApp group. In 5 minutes, we will be sharing one link. I request you to please go through the link and provide your valuable inputs. Thank you. Thank you, Puneet, sir. So we will be connecting back by 3 p.m., sir.
All right.
Yeah. Thank you.
Am I audible?
Yes, sir.
Oh,
Yeah.
thank you.
Yes,
Thank you.
Gaurav.
Hello. Namaskar, love sir. Namaskar, Puneet ji.
Hi.
Namaskar, Ji.
Namaskar,
Namaskar,
Gaurav ji.
Vicky.
Namaste, sir.
So, I hope things are fine.
Yes, I hope everything is fine there also because we are reading very disturbing news about the situation in Assam, floods and all.
Yeah, Assam floods actually, it's every year. And I think now the time has come when government should take a proper precaution and like things so that flood can should not disturb us again and again. But it's a problem all the time. You're right.
And you are right there on the bank of the river.
Yeah, and in fact, I am not able to go out to see how my Brahmaputra has come up because IIT Guwahati has 4 COVID care hospitals inside the campus.
Oh,
So we are actually living just almost like we are almost living in a hell actually, and a very scary environment for us, and can't say anything more.
oh no, I can well realize. And hats off to you that in such difficult circumstances, you and your team, Firuzaji and all, they have pulled off a real good course.
Thank
So,
you.
my
I'm to say,
congratulations.
yeah, I'm to say I just you can say thanks to the entire team led by Froja. They really have done a very good you can
Oh,
say.
yes, your complete team has done an excellent job because I was seeing whatever messages and whatever is happening to
Mhm.
have a proper evaluation. Everything in this environment is not easy. Managing everything is requires real good teamwork and a real good leader.
Thank you, sir. In fact, I just say that I'm to say I just say that specifically this thing. What should I say? Intel and Mentor actually they have really done a good job. I'm to say without their support, uh, we really actually couldn't have reached up to this level. Their support was very much necessary.
No, that's true because with this providing the support word and they are providing from so many places coordinating and having such a thing and experts sparing time for this course. So I'm sure for the participants it must have been a real good learning experience
Yeah.
and that would be reflected in the feedback.
So I think so. So, Froja, should we wait for a little bit more and or shall we
Yeah,
start?
yeah. Good afternoon, sir. Sir, actually, we are just waiting for Israr sir to join. And
Okay.
sir, just 2 minutes, sir. We are making everyone connected. So just give us 2 minutes, sir. We are
No,
doing
no,
this.
no problem. No.
Thank you, sir.
Thank
Sir, should I display the feedback statistics if possible, so that you can just
Can you, yeah,
have a look?
can you please send it to me once?
Yeah, sir. I'm just forwarding you the details. Yes, sir. 2 minutes, sir. I'm giving you.
Uh, Ratnesh sir is joining Froja. Bhuvali, can you please for Ratnesh sir?
No, sir. Actually, sir told me to continue because sir is maybe busy with some work. So, sir told me to please request Gaurav sir to continue. He will try to join if he gets free, sir.
Mm-hmm. Okay. Okay.
Thank you, sir.
Okay.